Right now, Texas is building bigger and bolder than almost anywhere else in the world. From high-speed rail systems and billion-dollar freeways to energy giants rising in the desert, these megaprojects are transforming the Lone Star State in real time. Today, we reveal Texas's megaprojects under construction and why what's happening here is setting the tone for the future of American infrastructure. The Harbor Bridge Replacement Project in Corpus Christi, Texas, represents one of the most ambitious infrastructure endeavors in the region, designed to replace the original bridge constructed in the mid-1950s. The new structure is engineered as a cable-stayed bridge, designed not only to accommodate increased traffic loads, but also to provide greater navigational clearance for maritime traffic. The new bridge will span approximately 1,661 feet across the Corpus Christi Ship Channel, featuring a main span that will be one of the longest of its kind in the United States. The project includes the demolition of the existing bridge, construction of approach roads, interchanges, and the bridge itself, which is expected to dramatically improve safety, traffic flow, and economic opportunities in the region. Site preparation began with extensive geotechnical investigations to assess subsurface conditions, followed by clearing and grading of the surrounding area to make way for construction activities. Deep foundation systems, primarily composed of reinforced concrete drilled shafts, were constructed to anchor the massive support towers of the cable-stayed span. These shafts extend over 100 feet below ground to ensure stability in the coastal environment, where soil conditions include a mix of clay, sand, and silt with high water tables. The main pylons, rising over 500 feet into the air, were constructed using high-strength reinforced concrete and required precision formwork and climbing form systems to maintain alignment during vertical construction. Simultaneously, the precast segmental approach spans were fabricated off-site and transported to the site for assembly. Each segment, weighing several tens of tons, was lifted into place using specialized launching gantries and strand jacks. The stay cables, which are the defining characteristic of the bridge's design, were installed in a carefully sequenced process to balance loads and prevent excessive stress on the partially completed structure. Each cable bundle was tensioned to precise specifications using hydraulic jacks, ensuring structural integrity and minimizing deflection. Logistical challenges included coordination with ongoing port operations, maintaining traffic flow during construction, and ensuring compliance with stringent environmental regulations protecting the adjacent wetlands and water bodies. Advanced monitoring systems were embedded within the structure to track stress, displacement, and vibrations throughout the life of the bridge. Upon completion, the new Harbor Bridge will not only serve as a critical transportation link, but also stand as a landmark of modern engineering achievement on the Gulf Coast. The Port Arthur LNG terminal is a large-scale liquefied natural gas export facility currently under construction along the Gulf Coast in Port Arthur, Texas. This megaproject is designed to transform natural gas into its liquefied state for efficient overseas transport, requiring a complex assembly of process infrastructure, storage systems, marine loading capabilities, and supporting utilities. The site spans hundreds of acres and is being developed in multiple phases, with the initial phase encompassing 2 liquefaction trains, each capable of processing approximately 6.5 million metric tons of LNG per year. The project's scope includes heavy civil works, advanced cryogenic systems, and extensive marine infrastructure, all of which demand high levels of precision and coordination. Construction began with extensive site preparation, involving the clearing of existing vegetation, deep soil stabilization using lime and cement-treated soils, and the installation of dewatering systems to manage the high groundwater levels typical of the Gulf Coast region. Excavation and grading operations ensured the site met the precise elevation and drainage requirements necessary to support the heavy process equipment and prevent flooding during severe weather events. Foundations for the massive liquefaction trains and LNG storage tanks were constructed using deep pile systems, typically involving steel pipe or precast concrete piles driven to depths exceeding 100 feet to reach load-bearing strata. Above these, large reinforced concrete pile caps and slabs provided stable bases for mounting compressors, heat exchangers, and ancillary equipment. The LNG storage tanks themselves are double-walled, full containment structures composed of inner nickel-steel tanks designed to handle cryogenic temperatures and outer pre-stressed concrete shells that offer structural protection and containment in case of leaks. Installation of the liquefaction equipment required precision alignment of turbo expanders, cryogenic heat exchangers, and gas turbines, all interconnected through high-alloy piping systems built to withstand extremely low temperatures and high pressures. Welding and non-destructive testing followed rigorous standards to ensure system integrity, particularly where thermal cycling could induce material fatigue. Marine infrastructure construction included dredging of berths and turning basins, driving of large-diameter mooring and breasting dolphins, and installation of loading arms capable of transferring LNG from the terminal to specialized carriers. Safety systems were integrated throughout the facility, including emergency shutdown valves, gas detection systems, and blast-resistant control buildings. Upon completion, the Port Arthur LNG terminal will serve as a key export hub, contributing significantly to the global LNG supply chain and demonstrating advanced capabilities in industrial-scale cryogenic engineering. The Golden Triangle Polymers Project is a significant petrochemical development located in Orange County, Texas, designed to produce polyethylene from ethane feedstock derived from natural gas. This multi-billion-dollar facility includes a world-scale ethane steam cracker and several polyethylene production units, intended to supply high-performance plastic resins for global markets. The project's name is derived from the local region known as the Golden Triangle, a historically industrialized area defined by the cities of Beaumont, Port Arthur, and Orange. Construction of this complex involves massive civil, structural, mechanical, and electrical works, integrating advanced process technologies with robust environmental and safety systems. Site development commenced with bulk earthworks, where tens of thousands of cubic yards of soil were excavated, compacted, and leveled. Ground improvement techniques such as surcharge preloading and deep soil mixing were employed to mitigate settlement risks due to the area's soft, compressible soils and high water table. A dense network of underground utilities, including stormwater drainage, fire water lines, and chemical-resistant process sewers, was installed beneath reinforced concrete foundations that support the heavy process equipment. The ethane cracker, the core of the facility, operates by heating ethane to over 1,500 degrees Fahrenheit in large cracking furnaces. These furnaces were assembled on deep foundations and equipped with radiant coils and convection sections fabricated from high-temperature alloys. The cracked gas is then rapidly quenched to halt the reaction, routed through a series of compressors, and subjected to cryogenic separation processes to isolate ethylene from other hydrocarbons. This required the construction of tall distillation towers, complex heat integration systems, and high-pressure ethylene pipelines, all of which demanded exacting tolerances and strict adherence to process safety protocols. The polyethylene units downstream involve polymerization reactors, pelletizers, and storage silos. Each unit required precise mechanical installation, including the alignment of extruders and gear pumps, supported by large structural steel frameworks and enclosed in metal-clad buildings with integrated ventilation and dust collection systems. Electrical works included high-voltage substations, cable tray networks spanning miles, and process automation systems featuring thousands of field instruments connected to a centralized distributed control system. Construction logistics were coordinated through modularization strategies, with prefabricated pipe racks, equipment skids, and control rooms transported to the site and lifted into position using heavy lift cranes. The facility also features a dedicated rail and truck loading infrastructure for product distribution. Upon completion, the Golden Triangle Polymers Project will reinforce the region's standing as a global center for chemical manufacturing, leveraging abundant natural gas resources and state-of-the-art engineering to produce essential plastic materials. The Southeast Connector is a major highway reconstruction and expansion project taking place in Tarrant County, Texas, aimed at upgrading approximately 16.5 miles of transportation infrastructure across one of the busiest corridors in the Dallas-Fort Worth metropolitan area. The corridor includes portions of Interstate 20, Interstate 820, and U.S. Highway 287, serving as a critical east-west and north-south link for both commuter and freight traffic. This design-build project involves extensive demolition, earthwork, bridge construction, pavement replacement, and the addition of new general-purpose lanes and collector-distributor systems. Construction activities began with the mobilization of heavy equipment and the establishment of traffic control measures to safely maintain vehicular flow through active work zones. Initial phases involved the demolition of existing overpasses, barrier walls, and deteriorated pavement sections. Earth-moving operations followed, with mass excavation and embankment fills to realign roadway grades and prepare for widened sections. Subsurface utility investigations and relocations were performed in tandem to clear the path for foundational work. Bridge construction represents a significant component of the project, requiring the erection of dozens of new overpasses and flyover ramps. Deep foundations using drilled shafts and driven piles were installed to support substructures, followed by the placement of reinforced concrete columns and bent caps. Precast concrete girders were set in place using high-capacity cranes, and bridge decks were formed and poured using slip-form paving techniques. Extensive staging was required to minimize traffic disruptions, with nighttime and weekend closures strategically utilized for critical lifts and beam placements. In terms of roadway improvements, the project includes the addition of multiple new lanes to accommodate future traffic demands, with continuous steel-reinforced concrete pavement sections designed for durability under high-load conditions. Collector-distributor roads were constructed alongside main lines to improve interchange efficiency and reduce weaving conflicts. Frontage roads were also expanded, and new ramps were introduced to facilitate better access and egress at key junctions. Drainage systems, including concrete box culverts, storm sewers, and detention basins, were constructed to manage stormwater runoff and prevent flooding. Intelligent transportation systems such as dynamic message signs, traffic cameras, and vehicle detection systems were integrated throughout the corridor to enhance real-time traffic monitoring and incident response. Sidewalks and shared-use paths were included to support pedestrian and bicycle access, aligning with broader goals of multimodal connectivity. Scheduled for completion in 2028, the Southeast Connector is poised to significantly reduce congestion, enhance safety, and support economic growth by upgrading a vital section of Texas's highway network with modern engineering solutions and long-term capacity improvements. The East Blackland Solar Project, located in Travis County, Texas, is a utility-scale photovoltaic power generation facility designed to harness solar energy through the deployment of high-efficiency solar panels across several hundred acres of land. The project is part of a broader strategy to expand renewable energy capacity in Central Texas and contributes to grid reliability and emissions reduction targets by providing clean electricity to the regional power market. Construction of the facility began with comprehensive site assessments to evaluate solar irradiance, soil stability, drainage patterns, and potential environmental impacts. Land preparation included grading to create a uniform slope for optimal panel alignment, followed by the installation of erosion control measures, such as silt fences and retention basins to manage stormwater during construction. Once the site was cleared and stabilized, trenching operations commenced to lay underground conduit for power and communications cabling, which would later connect the solar arrays to inverters and switchgear. The racking systems, which support the photovoltaic panels, were constructed using galvanized steel posts, driven into the ground at regular intervals. These posts were installed with hydraulic pile drivers, calibrated to maintain precise verticality and depth. The project utilized single-axis tracking technology, which allows solar panels to follow the sun's path across the sky, thereby maximizing energy production. The tracking systems were assembled on the support structures and equipped with actuators and controllers programmed to adjust panel tilt based on real-time solar position data. Photovoltaic modules were mounted in rows on the racking systems with electrical connections made in series to form strings, which were then aggregated into combiner boxes. From there, direct current electricity was routed through underground cables to centralized inverter stations, where it was converted into alternating current. Each inverter station included transformers, switchgear, and protective relays designed to manage voltage regulation, grid synchronization, and fault protection. A high-voltage substation was constructed on site to step up the electricity to transmission-level voltages and interconnect it with the local utility grid. This substation included power transformers, circuit breakers, and transmission line takeoff structures, all built to utility specifications. The entire site was enclosed with security fencing and equipped with monitoring systems, including weather stations and real-time data acquisition platforms that allow operators to track performance metrics and remotely manage the system. Upon completion, the East Blackland Solar Project became a key renewable energy asset for the region, demonstrating the scalability and reliability of solar technology in utility applications and supporting the ongoing transition toward a more sustainable energy infrastructure. The Giga Texas expansion, taking place at Tesla's sprawling manufacturing campus near Austin, Texas, represents a significant scaling effort aimed at boosting production capacity across multiple vehicle lines, battery systems, and structural components. Originally developed as a massive integrated factory for Model Y and Cybertruck production, the expansion adds several million square feet of manufacturing space, auxiliary facilities, and infrastructure to accommodate increased throughput and new production technologies. Construction activities began with clearing and earthworks on adjacent parcels of land to the existing plant, involving extensive excavation, grading, and soil stabilization to create uniform building pads capable of supporting heavy industrial structures. To counter the region's expansive clay soils, foundation work employed deep-drilled piers and reinforced concrete mat slabs. In some areas, ground improvement measures such as lime stabilization and geotextile reinforcement were used to enhance load-bearing capacity and mitigate settlement risks. The structural steel framework for the new buildings was erected using high-capacity cranes and modular assembly techniques to expedite construction timelines. Prefabricated steel columns, beams, and joists were bolted and welded into place, forming large-span bays that allow for uninterrupted production floor layouts. Roof systems were installed using insulated metal panels or single-ply membrane systems, supported by lightweight purlins and designed to accommodate mechanical units, skylights, and solar arrays. Interior construction followed a just-in-time approach, with mechanical, electrical, and plumbing trades coordinating installations to align with equipment delivery schedules. High-voltage electrical rooms, compressed air systems, process cooling loops, and ventilation ducts were integrated alongside the structural envelope. Specialized utility trenches were installed throughout the production halls to support robotic assembly lines, material handling conveyors, and automated guided vehicle systems. Battery production areas were fitted with climate-controlled environments, explosion-proof fixtures, and dry rooms with dehumidification systems to meet strict environmental controls required for lithium-ion cell manufacturing. These spaces required isolated foundations and vibration-damping floor assemblies to support precision machinery for electrode coating, cell assembly, and electrolyte filling. Additional facilities constructed as part of the expansion include logistics hubs, employee amenities, research labs, and test tracks. Roadways, stormwater detention ponds, and utility corridors were extended to support the new buildings, with site-wide infrastructure upgraded to handle the increased power demand and data connectivity. The expansion also incorporated sustainability elements such as rainwater harvesting, rooftop solar integration, and energy-efficient lighting systems. Once fully operational, the Giga Texas expansion will elevate the site's role as a central node in Tesla's manufacturing network, significantly increasing output across vehicle, battery, and structural component lines, while embedding advanced automation and vertically integrated production strategies into the facility's growing footprint. The Terminal B modernization project at George Bush Intercontinental Airport in Houston is a comprehensive reconstruction effort aimed at transforming one of the airport's oldest terminals into a modern facility that meets current and future demands for domestic regional air travel. The modernization spans structural, architectural, mechanical, and technological upgrades across both the north and south concourses, significantly enhancing passenger experience and operational efficiency. The project began with demolition activities focused on aging infrastructure, including removal of outdated gate structures, baggage systems, mechanical rooms, and interior finishes. Careful sequencing allowed active terminal operations to continue throughout construction, with temporary walls and rerouted passenger pathways maintaining secure access zones and minimizing disruptions. Heavy demolition equipment was mobilized during nighttime shifts to dismantle structural components, followed by hauling of debris off-site and preparation of new construction zones. New foundations were laid using reinforced concrete footings and grade beams supported by drilled piers to address the expansive clay soils common in the Houston area. Structural steel framing was erected to form the skeleton of the expanded concourses, designed to support taller ceilings and larger open-span interiors. Lateral stability was achieved using cross-bracing and moment frame assemblies, ensuring the building could withstand high wind loads typical of Gulf Coast storms. Architectural improvements included curtain wall systems with energy-efficient glazing, metal panel cladding, and expanded roof canopies. The terminal was outfitted with high-efficiency HVAC systems, LED lighting, and building automation systems integrated through a centralized control platform. Interior finishes were selected for durability and aesthetics, featuring terrazzo flooring, stainless steel accents, and acoustic ceilings to manage noise levels in busy passenger areas. Gate areas were redesigned to accommodate dual boarding bridges for regional jets and larger aircraft, with apron modifications including new fuel pits, storm drains, and aircraft service utilities. The baggage handling system was fully replaced with a high-speed, RFID-enabled conveyor network that streamlines sorting and routing. Mechanical rooms were upgraded with variable frequency drive pumps, chillers, and air handling units, sized to meet the demands of modern terminal operations. Passenger amenities such as expanded seating areas, charging stations, restrooms, concessions, and signage were all reimagined to provide a seamless and intuitive travel experience. Security screening areas were reconfigured to improve throughput and align with TSA's latest technology standards, incorporating automated bin return systems and integrated body scanners. Upon completion, the Terminal B modernization will significantly boost capacity for United Airlines and regional carriers, transforming the terminal into a state-of-the-art hub equipped to handle millions of passengers annually with increased comfort, efficiency, and architectural sophistication. The Northeast Lakeview College expansion in New Braunfels represents a major investment in regional higher education infrastructure, aimed at addressing increasing enrollment demands and enhancing accessibility for students across Comal County and surrounding areas. This project involves the comprehensive renovation and adaptive reuse of a pre-existing 58,000 square foot commercial structure, formerly occupied by a financial institution, into a fully functioning academic center designed to support a broad range of instructional programs and student services. Construction activities commenced with selective interior demolition to remove non-load-bearing partitions, obsolete mechanical systems, and outdated finishes. This was followed by structural assessments to ensure the existing building shell could accommodate new loads introduced by academic programming. Reinforcement of floor slabs and roof structures was carried out where necessary, particularly in areas designated for heavy equipment such as laboratory installations and mechanical units. Mechanical, electrical, and plumbing systems were entirely overhauled. A new rooftop HVAC system with variable air volume controls was installed to ensure optimal thermal comfort and energy efficiency across diverse instructional spaces. Electrical upgrades included new panel boards, LED lighting fixtures, and structured cabling to support campus-wide Wi-Fi and integrated classroom technologies. Plumbing infrastructure was expanded to serve additional restrooms, science labs, and break areas, with low-flow fixtures and hot water recirculation systems incorporated to reduce water consumption. Interior build-out included the construction of general-purpose classrooms, computer labs, science laboratories with fume hoods and gas piping, faculty offices, and multi-use student spaces. Specialized instructional areas were outfitted with flexible furnishings, audio-visual systems, and digital teaching tools compatible with hybrid learning formats. Acoustical treatments such as suspended ceiling panels, wall baffles, and sound-isolating doors were used throughout the facility to maintain a conducive learning environment. Accessibility upgrades brought the building into compliance with the Americans with Disabilities Act, including the installation of a new elevator, widened doorways, tactile signage, and accessible restroom facilities. The entry and exit points were redesigned with automated doors and weather protection canopies, and site work improvements included new sidewalks, AD-compliant parking, landscaping, and stormwater management systems. The project also involved the addition of a new fire protection system, including sprinklers and a fire alarm network, fully integrated into the college's safety protocols. Security enhancements included controlled access points, surveillance cameras, and emergency communication systems. Once operational, the expanded Northeast Lakeview College campus in New Braunfels will serve as a vital educational hub, providing state-of-the-art facilities and instructional capacity to support the growing academic needs of the region. The Northern Corridor roadway projects in Frisco, Texas, represent a comprehensive infrastructure initiative aimed at accommodating the city's rapid growth and enhancing transportation efficiency. With an investment exceeding $200 million, the city is undertaking 10 major roadway construction and improvement projects, encompassing over 65 miles of new and upgraded roadways. These projects are strategically distributed throughout the Northern Corridor, particularly within the expansive Fields development, a 2,500-acre master-planned community. Construction activities began with extensive site preparation, including land clearing, grading, and the installation of erosion control measures to stabilize the terrain. Subsurface investigations were conducted to assess soil conditions, informing the design of robust foundation systems capable of supporting the anticipated traffic loads. Utility relocation efforts were coordinated to ensure uninterrupted services during the construction phases. Key projects include the widening and extension of Panther Creek Parkway, transforming it into a 6-lane divided roadway to improve east-west connectivity. This involved the construction of new pavement sections, stormwater drainage systems, and the installation of traffic signals at major intersections. Similarly, the expansion of Legacy Drive and Fields Parkway required the reconstruction of existing roadways, incorporating additional lanes, medians, and pedestrian pathways to enhance safety and capacity. The Dallas North Tollway is undergoing significant reconstruction, with more than 18 miles of main lanes being widened to accommodate increasing traffic volumes. This complex operation necessitated the use of advanced construction techniques, such as phased construction to maintain traffic flow, the deployment of high-capacity cranes for bridge beam placements, and the implementation of intelligent transportation systems for real-time traffic management. Frisco Street North is being developed as a new 2-lane roadway connecting Universal Parkway to PGA Parkway. This project includes the construction of a new roadway base, asphalt paving, and the integration of signage and lighting systems to meet modern roadway standards. The design also incorporates provisions for future expansion, anticipating continued growth in the area. Throughout the corridor, attention is given to multimodal transportation options. Sidewalks, bike lanes, and shared-use paths are being integrated into the roadway designs, promoting alternative modes of transportation and enhancing community connectivity. Landscaping efforts, including the planting of native vegetation and the installation of irrigation systems, are also underway to improve the aesthetic appeal of the corridors. The Waterline Tower in Austin, Texas, is an ambitious high-rise construction project that, upon completion, will become the tallest building in the state. Rising to a height exceeding 1,000 feet, this mixed-use skyscraper is engineered to accommodate residential units, a luxury hotel, office spaces, and retail areas, all within a compact downtown footprint adjacent to Lady Bird Lake. The complexity of the tower's design and construction stems from its height, slender profile, and the integration of diverse occupancy types across its vertical structure. Initial construction began with deep excavation and shoring to enable installation of a mat foundation capable of distributing immense structural loads across Austin's variable limestone and clay subsoils. Foundation work included the drilling of reinforced concrete piers extending more than 100 feet into bedrock, coupled with a heavily reinforced concrete mat that was poured in a single continuous operation, requiring logistical coordination of multiple concrete batch plants and continuous pumping over several days. The building's superstructure is composed primarily of a high-strength reinforced concrete core, which houses vertical transportation systems and provides torsional stability against wind and seismic forces. Outrigger and belt truss systems are integrated at mechanical levels to distribute lateral loads across the perimeter columns, enhancing structural rigidity. The core was constructed using a self-climbing formwork system, allowing for continuous vertical progress without reliance on external scaffolding, while steel and concrete composite floor systems were constructed simultaneously to minimize schedule duration. Mechanical, electrical, and plumbing systems are vertically stacked in dedicated shafts with strategically located mechanical floors to ensure efficient distribution and maintenance access. High-efficiency chillers, low-flow plumbing fixtures, and advanced lighting controls are integrated as part of the building's sustainable design approach, targeting LEED certification. Art House in St. Petersburg, Florida, is a contemporary high-rise residential tower designed to bring sophisticated urban living to the downtown waterfront. Rising prominently within the city's growing skyline, this tower combines modern architectural aesthetics with state-of-the-art structural systems and high-end residential amenities. From an engineering and construction standpoint, Art House presents a complex project involving deep foundation systems, vertical construction sequencing, and advanced building envelope technologies tailored to a subtropical coastal climate. The project began with comprehensive site preparation and geotechnical analysis to evaluate subsurface conditions typical of coastal Pinellas County. Due to the high water table and relatively soft soils in the area, a deep foundation system was required. Construction teams employed auger-cast piles or drilled shafts, installed using heavy drilling rigs equipped with continuous flight augers, which placed concrete and reinforcing steel deep into the ground to reach stable soil strata. Dewatering operations were necessary throughout foundation work, with well point systems operating continuously to maintain dry working conditions below grade. Once the pile caps and grade beams were completed, the project transitioned to vertical construction, starting with the building's reinforced concrete core. This central structural element was constructed using jump form systems, rising level by level ahead of the floor slabs. Each floor slab was built using post-tensioned concrete, providing long spans and open layouts ideal for luxury condominiums. Structural engineers designed the lateral load-resisting system with shear walls and moment frames to withstand wind pressures consistent with hurricane-prone areas. Mechanical, electrical, and plumbing systems were integrated through centralized vertical risers, with separate zones serving individual residential units. The HVAC system incorporated energy-efficient air handlers, dehumidification components, and smart thermostatic controls. Plumbing systems were pressure-tested at each level, and sound insulation was installed around vertical ducts and pipe chases to maintain acoustic separation between units. The exterior cladding of Art House consisted of a high-performance curtain wall system and impact-rated glass, engineered to provide thermal insulation and wind resistance while maximizing panoramic views. Installation required the use of suspended platforms and tower cranes, with each unit sealed and waterproofed before interior work proceeded. Balcony structures were cantilevered and waterproofed using multi-layer membranes, with drainage integrated to manage Florida's heavy rainfall. Interior finishes followed a high standard, including European cabinetry, engineered hardwood flooring, quartz countertops, and custom lighting. Coordination of trades during the interior build-out phase was tightly scheduled, with finish carpenters, electricians, tile setters, and painters working in controlled sequences to meet aesthetic and performance standards. Fire protection systems, including sprinklers and emergency lighting, were installed and tested in compliance with local and national codes. The amenities level included a pool deck, fitness center, resident lounges, and workspaces, all requiring precise structural coordination to support loads from water, occupancy, and specialized equipment. Mechanical penthouses and service rooms were constructed on the uppermost levels, housing HVAC units, water heaters, and electrical switchgear, all enclosed within louvered screens for both visual appeal and sound attenuation. Logistics for the entire project were managed within the constraints of a dense urban environment. Construction staging, crane placement, material deliveries, and worker access were choreographed daily to minimize disruption to surrounding businesses and pedestrian pathways. Strict safety protocols and regular inspections ensured compliance throughout the build, with attention to stormwater runoff control and debris containment given the proximity to Tampa Bay. Situated in the heart of Southeast Texas's industrial corridor, the Golden Triangle Polymers project represents a major advancement in the Gulf Coast's petrochemical manufacturing capacity. This massive facility is being constructed to produce polyethylene and other polymer products from ethylene feedstock derived from natural gas liquids. The project begins with the development of a multi-acre greenfield site, requiring extensive earthwork, drainage management, and foundation preparation across terrain with high groundwater and soft, compressible soils. Soil stabilization techniques include the use of lime or cement treatment and surcharge fills to achieve acceptable bearing capacities for large process structures. Deep foundation systems are essential to support the heavy loads imposed by vertical vessels, reactor units, and compressor modules. Construction crews installed drilled piers and driven piles to depths exceeding 100 feet, with precision tolerances ensured through the use of GPS-guided rig systems and real-time monitoring during installation. Once foundations are completed, concrete pads and structural steel framing are erected to house process units such as cracking furnaces, separation columns, and polymerization reactors. These are built using modularized construction strategies, where large components are fabricated off-site, shipped by barge or heavy-haul truck, and lifted into position by crawler cranes with lifting capacities over 1,000 tons. The core production process centers around the ethane cracking furnaces, which convert ethane into ethylene through high-temperature thermal decomposition. These furnaces are complex assemblies of fireboxes, radiant tubes, and convection sections, all requiring precise refractory lining and thermal insulation. The resulting ethylene gas is rapidly quenched and routed to distillation columns where it is separated from byproducts under carefully controlled pressures and temperatures. Polymerization units downstream transform ethylene into polyethylene pellets through catalyst-induced chain reactions inside high-pressure reactors. These areas are designed with extensive piping, instrumentation, and control systems to maintain strict process parameters. Each reactor line is supported by a network of utility systems, including nitrogen generation, compressed air, cooling water, and steam distribution, all interconnected through color-coded pipe racks spanning hundreds of feet. Electrical power for the facility is delivered via high-voltage substations and switchgear buildings, incorporating redundant feeds and uninterruptible power supplies for critical control and safety systems. Distributed control systems and programmable logic controllers operate from a central control room, managing process sequencing, alarms, and interlocks. Fiber optic networks connect instrumentation throughout the site to provide real-time monitoring and diagnostic capabilities. A significant part of the construction effort is dedicated to environmental compliance and emissions control. Flare systems, vapor recovery units, and wastewater treatment plants are installed to capture and process effluents, ensuring the plant meets federal and state environmental standards. Additionally, fire protection systems, including foam suppression, hydrants, and emergency deluge zones, are integrated throughout the site to mitigate risks associated with flammable materials. Upon completion, commissioning and startup procedures involve comprehensive testing of mechanical systems, loop checks of instrumentation, safety interlock validation, and initial product runs under controlled conditions. The Golden Triangle Polymers project, once operational, will stand as a cornerstone in the region's industrial landscape, combining large-scale chemical engineering with advanced construction practices and operational precision. At the heart of a massive urban revitalization effort, the Willets Point Soccer Stadium project emerges not only as a sports venue, but as a key piece of a complex redevelopment puzzle. Constructing a state-of-the-art stadium on a site formerly known for auto repair shops and contaminated soils involves far more than vertical construction. The first challenge is transforming the ground itself into a buildable foundation, a process requiring rigorous environmental remediation and extensive geotechnical preparation. Before any structural work begins, the site undergoes excavation of contaminated fill material, which includes petroleum-impacted soil and debris. Specialized crews follow a strict chain of custody protocol for soil sampling, segregation, and disposal. Remediation often involves the removal of several feet of surface material, followed by the installation of engineered fill and geotextile layers to cap and isolate any remaining residual contaminants. Groundwater treatment systems may also be installed to intercept and treat subsurface flow if hydrocarbon plumes are detected. Stadium construction begins with deep foundations, which are essential due to the site's prior use and potentially unstable subsurface conditions. A combination of drilled shafts and auger cast piles are used, designed to transfer loads through weaker upper strata into competent soil or rock layers well below grade. These piles are tested with static and dynamic load tests to confirm bearing capacity before concrete pile caps and grade beams are formed to create the structural base. The superstructure consists of a structural steel frame, prefabricated in sections off-site and trucked in for assembly using heavy lift cranes. Each piece is set into position using bolted connections and moment frames, forming a rigid skeleton for the seating bowl and roof structure. The stadium bowl is composed of precast concrete risers supported by steel raker beams, allowing rapid installation while ensuring consistency in alignment and dimensions. Vomitories, stair towers, and elevator cores are cast in place using high-strength concrete, reinforced with rebar cages tied and inspected on site. Roof systems vary by design, but for a stadium in this urban context, lightweight cantilevered trusses often support ETFE panels or metal decking to provide coverage without excessive shadowing or bulk. The cantilevers require counterweights or tension cables anchored deep into the structure to manage wind loads and uplift. Drainage systems are integrated into the roofing and seating areas to divert stormwater into underground retention systems, complying with city runoff regulations. Interior spaces such as locker rooms, concession areas, and mechanical rooms are built out once the primary structure is weather-tight. MEP systems are installed in coordination with architectural finishes, with central plant systems located in below-grade spaces or adjacent utility buildings. Electrical distribution includes robust conduit networks for lighting, broadcast infrastructure, and stadium-wide Wi-Fi systems. The playing field itself is constructed with precision grading and layered subsurface drainage. A sand-based root zone supports natural grass or hybrid turf, depending on the final performance criteria. Subsurface heating and irrigation systems are installed beneath the field surface, connected to central control units to maintain optimal playing conditions year-round. Completing the stadium includes extensive public realm improvements, sidewalks, plazas, lighting, and transit integration, transforming what was once industrial backland into a civic gathering place built to host tens of thousands of fans in a structure defined by engineering discipline and urban transformation. In the vast and rugged terrain of western Nevada, the Greenlink West Transmission Line project began with a series of extensive environmental and geotechnical surveys. This corridor, stretching hundreds of miles, demanded careful route selection to avoid sensitive habitats, archaeological sites, and unstable soil zones. Once the alignment was finalized, crews mobilized with access road grading as the first priority. In remote desert areas, temporary haul roads and helicopter pads were established to enable movement of personnel, equipment, and materials to tower sites that had no existing access. Tower foundations varied depending on soil conditions. In rocky upland zones, foundation crews used blast hole drilling, followed by concrete anchors set deep into fractured bedrock. In softer or sandy valley floors, deep bored shaft foundations were poured with reinforced concrete, sometimes with steel casing to prevent wall collapse. Each foundation was designed to handle both axial and lateral loads imposed by conductor tension and wind shear on the towers. Concrete had to be batched locally or transported in rotating mixers across significant distances, requiring careful coordination to ensure consistency and curing integrity. The transmission towers themselves were largely lattice steel structures, fabricated off-site and delivered in sectional bundles. Erection crews used tracked cranes where terrain allowed, while in the steepest sections, helicopters were employed to lift tower segments into place. Ground crews then bolted the segments together using high-strength structural fasteners. Each tower was surveyed post-erection for verticality and alignment, using laser theodolites before conductor stringing began. Conductor installation involved multiple phases. First, pilot lines were pulled between towers using drones or helicopters. These were then used to draw in heavier steel messenger cables, which in turn pulled in the high-voltage conductor bundles. Each conductor was tensioned using hydraulic pullers and tensioners to exact sag tolerances specified in the design documents. Spacer dampers were installed at calculated intervals to prevent aeolian vibration, and insulators, often made from composite polymer materials, were mounted to separate the live conductors from the grounded towers. Substations on either end of the line required massive transformers, circuit breakers, and control systems to manage voltage conversion and grid integration. These substations were built concurrently, with site grading, pad installation, and bus work assembly proceeding, while the main line was being erected. The Greenlink West project not only involved transmission infrastructure, but also included communications fiber installation and SCADA integration for remote monitoring, forming a backbone for a more resilient and renewable-focused power grid across the region. From the foundation to the rooftop, every phase of the 1,000 Museum's construction demanded attention to detail, precision, and innovative engineering. It stands not just as an architectural landmark, but as a testament to what is achievable when complex geometry, structural necessity, and construction craft are woven together into a seamless vertical composition. Few transportation projects in recent American history and the construction of entirely new track alignments through dense urban areas, sensitive wetlands, and heavily trafficked transportation zones. From the earliest design phase, engineers had to account for a range of technical challenges, from grade separation and drainage. In contrast, the northern portion from West Palm Beach to Orlando International Airport involved new greenfield construction through undeveloped terrain. Crews cleared and grubbed hundreds of acres, rerouted surface water channels, and installed wildlife crossings in environmentally sensitive areas. Earthwork was extensive. Embankments and cut sections were designed to minimize gradients and allow for smooth acceleration and braking curves. The right-of-way was protected by a combination of fencing, access controls, and overpasses to eliminate at-grade crossings, critical for both safety and operational efficiency. Bridges and viaducts represented key components of the alignment, especially at major road crossings and river spans. Precast concrete girder bridges were deployed using accelerated bridge construction techniques. Piers were founded on deep-drilled shafts, many of which had to be constructed under challenging conditions involving soft soils and high groundwater levels. Certain elevated sections used segmental box girders cast in place and post-tensioned, allowing for long spans and reduced support footprint. These elevated guideways also helped mitigate environmental impact in flood-prone areas and reduce the need for extensive land acquisition. One of the most technically intensive elements was the implementation of a positive train control system across the corridor. This safety-critical layer included continuous GPS-based tracking, wireless communication between locomotives and control centers, and real-time enforcement of speed limits and signal compliance. Installation of the PTC system required the placement of signal houses, transponders, and fiber optic cable across the entire alignment, with redundant power sources and cybersecurity protections. The stations themselves, including the flagship terminals in Miami and Orlando, were designed as integrated multimodal hubs. Structural systems utilized long-span steel framing, while architectural cladding included aluminum composite panels, unitized glass curtain walls, and impact-resistant fenestration. Each station featured elevated platforms to streamline boarding, high-capacity vertical circulation elements, and advanced passenger information systems. Subgrade mechanical spaces housed electrical switchgear, HVAC chillers, and water reuse systems, all connected to centralized building management controls. Rolling stock was procured with an emphasis on energy efficiency, aerodynamic performance, and crash energy management. The train sets featured articulated cars with distributed traction motors, regenerative braking systems, and pressure-sealed cabins. Maintenance facilities along the corridor were equipped with drop pits, wheel lathes, and overhead cranes to support long-term fleet servicing. Throughout construction, scheduling and logistics were as crucial as engineering. Major portions of the corridor were built in active freight environments, requiring overnight possessions and strict coordination with existing operators. In urban areas, construction teams employed traffic diversion plans, temporary decking systems, and vibration monitoring to mitigate disruption to surrounding infrastructure. Environmental compliance was maintained through erosion control plans, wildlife monitoring programs, and wetland mitigation strategies. Ultimately, the completion of the Brightline Miami-Orlando high-speed rail line stands as a testament to integrated transportation engineering, blending high-performance rail systems with modern construction methodologies. The project not only introduces a new mode of intercity travel, but also sets a precedent for how private investment and infrastructure innovation can reshape mobility across regional scales.
American Dream Miami is an unprecedented megaproject designed to become the largest retail and entertainment complex in the United States. Located in northwest Miami-Dade County, the development spans hundreds of acres and merges commercial, recreational, and hospitality functions into a single, integrated site. The scale and ambition of the project require immense planning, phased construction sequencing, and coordination across multiple engineering disciplines including site civil works, structural engineering, vertical construction, and specialized systems for water management, traffic circulation, and energy efficiency. Site development began with mass grading and the relocation of existing utilities, involving the movement of millions of cubic yards of earth to create a stable foundation across what was once undeveloped wetlands and farmland. Environmental mitigation was a critical early phase component. Stormwater management systems were engineered with massive retention ponds, underground vaults, and bioswales to comply with South Florida Water Management District regulations. Sheet piling, soil stabilization with lime or cement treatments, and perimeter berm construction were necessary to prepare the site for heavy vertical loads and to ensure long-term ground stability, especially for areas designated to house water parks, ski slopes, and multi-story structures. The project's structural layout includes a network of interconnected buildings varying in height and use. Foundations for these buildings were engineered with both shallow and deep systems, depending on geotechnical conditions. Large-span structures like indoor amusement parks, water parks, and retail atriums required specialized deep-pile foundations to resist settlement and lateral movement. Steel framing with long-span trusses was employed extensively to create the large open interiors essential for attractions like roller coasters and wave pools. These components were fabricated off-site and assembled using heavy-lift cranes with precise sequencing to minimize schedule conflicts and allow concurrent work across multiple zones. Mechanical, electrical, and plumbing systems were designed to support massive peak loads generated by climate-controlled recreational areas, retail tenants, and food service zones. Chilled water systems with rooftop cooling towers, variable air volume handlers, and extensive ducting networks were installed to maintain climate conditions in enclosed amusement environments. Plumbing systems had to accommodate both typical domestic demand and specialized functions like indoor snowmaking and large-scale aquatics, necessitating high-capacity pumps, filtration systems, and corrosion-resistant piping. Exterior cladding and roofing systems were selected for both performance and branding, with components such as tensioned fabric structures, glass curtain walls, and themed facades constructed using modular prefabrication techniques. Waterproofing and insulation were layered to account for Florida's heat, humidity, and storm events, with roof drains and overflow systems engineered to handle extreme rainfall. Vertical transportation systems including high-capacity elevators, escalators, and people movers were integrated throughout the development to ensure accessibility and circulation for tens of thousands of daily visitors. Parking infrastructure was another engineering feat. Multi-level garages and expansive surface lots were constructed using post-tensioned concrete decks and cast-in-place retaining walls. Traffic engineering played a central role in designing ingress and egress routes, integrating on-site roads with regional highways through new interchanges, signalized intersections, and bus terminals. Intelligent traffic systems, signage, and wayfinding elements were planned with simulation-based modeling to prevent congestion and facilitate smooth vehicular and pedestrian movement. Construction logistics for American Dream Miami required a scale of coordination typically reserved for industrial megaprojects. Material delivery schedules, workforce housing, staging zones, crane paths, and safety barriers were modeled in 4D simulations to ensure optimal site utilization and risk mitigation. Simultaneously, environmental monitoring was carried out to assess air quality, water runoff, and noise levels, with mitigation strategies applied continuously during active phases of work. Once operational, the facility is designed to handle millions of visitors annually, with systems in place for emergency response, life safety, and operational redundancy. The construction of American Dream Miami reflects the most complex integration of vertical and horizontal engineering in a commercial setting, representing a new generation of hybrid destination centers that merge entertainment, retail, hospitality, and infrastructure into a cohesive engineered urban experience.
Serving as one of the largest and busiest airports in the world, the Dallas-Fort Worth International Airport represents a vast and intricately planned transportation infrastructure. The original construction of the airport began with the selection and preparation of an expansive site straddling the cities of Dallas and Fort Worth, requiring extensive grading, drainage systems, and soil stabilization over thousands of acres. Earth-moving operations included the redistribution of millions of cubic yards of soil to establish level runways, taxiways, and terminal zones, while ensuring compliance with strict FAA airfield geometry standards. The runways, which are among the longest in the country, were constructed in multiple phases using layered pavement systems. These include a stabilized subgrade, cement-treated base, and several layers of high-performance concrete capable of withstanding repeated heavy aircraft loads. Each runway incorporates lighting systems embedded in the pavement for approach, edge, and touchdown guidance, connected via underground conduits to airfield lighting control stations. Parallel taxiways are designed for optimal aircraft movement efficiency, with concrete paving sections built using slip-form pavers for tight tolerances and surface uniformity. Terminal construction involved erecting multiple large-scale structures with steel-framed superstructures and curtain wall systems composed of aluminum and high-efficiency glazing. Each terminal is equipped with multiple gate positions, connected to jet bridges, and supported by mechanical systems such as baggage handling conveyors, passenger boarding controls, and HVAC systems designed for high occupancy and variable loads. Subsurface utilities and automated train tunnels were constructed simultaneously, using cut-and-cover and bored tunneling methods to ensure interterminal connectivity without interrupting aircraft operations. The airport includes a central utility plant, constructed with chillers, boilers, and thermal energy storage tanks to provide efficient heating and cooling across the entire complex. Electrical substations and emergency backup generators are integrated into the system for uninterrupted power supply to critical operations such as runway lights, security systems, and air traffic control. To support intermodal transport, extensive roadways, bridges, and parking structures were built using pre-stressed concrete beams and deck slabs. Toll plazas and access control points are integrated with ITS systems for real-time monitoring and traffic regulation. Continuous expansion projects include terminal upgrades, runway extensions, and the integration of sustainability features such as solar panels, stormwater retention basins, and energy-efficient lighting. From a construction and engineering standpoint, Dallas-Fort Worth International Airport is a constantly evolving megastructure requiring phased construction strategies, airside-landside coordination, and specialized materials and systems to support safe and efficient global aviation operations. Constructing an academic building in the dense urban fabric of Manhattan presents challenges distinct from traditional campus development. The new academic building for the Fashion Institute of Technology had to reconcile limited lot dimensions, adjacent high-rise structures, and continual campus operations with the technical ambition of a vertically organized, highly specialized educational facility. From excavation to final systems commissioning, each stage of construction required precision scheduling, structural creativity, and adaptive coordination among trades. Foundation work commenced with site excavation bounded by existing college buildings and street infrastructure. Due to space constraints, materials handling was tightly regulated with just-in-time delivery protocols and vertical staging. The site was prepared with soldier pile and lagging retaining walls to stabilize the excavation before the deep foundations were installed. Given Manhattan's bedrock proximity, drilled shafts socketed into schist or spread footings on rock were employed, depending on the structural loading zones. The superstructure was framed using a reinforced concrete core combined with a structural steel skeleton, an approach balancing rigidity with floor plan flexibility. The core housed vertical circulation, bathrooms, and utility risers, cast in sequence to maintain construction momentum. The steel framing proceeded floor by floor, using mobile tower cranes erected within tight street setbacks. Fireproofing crews followed closely behind steel erection, applying spray-on materials in coordination with weather protection and enclosure installation. The building envelope emphasized energy performance and natural daylighting, incorporating high-performance curtain wall systems. These facades featured insulated glazing with low emissivity coatings, aluminum mullions with thermal breaks, and integrated solar shading elements. The installation of the curtain wall followed a sequential glazing process using swing stages and exterior lifts. Connections between the curtain wall and concrete slabs included thermal isolation pads and expansion joints to account for building movement and thermal cycling. Inside, the layout accommodated specialized spaces such as design studios, lecture halls, fabrication labs, and exhibition areas. Floor structures were reinforced and acoustically isolated in zones requiring heavy equipment or high sound attenuation. Interior partitions used cold-formed metal framing and high-density gypsum board, often layered with acoustic insulation or resilient channels in areas adjacent to classrooms or performance spaces. Mechanical, electrical, and plumbing systems were designed with adaptability and energy conservation in mind. Air handling units were located on mechanical floors and rooftop penthouses, serving variable air volume zones controlled by digital building management systems. Exposed ductwork in select areas supported the industrial aesthetic of design education environments while maintaining accessibility for maintenance. Hydronic heating and chilled water loops were integrated into the slab structure in certain areas, supporting radiant temperature control. Lighting design utilized daylight-responsive LED fixtures networked into a centralized control system. Occupancy sensors, dimming controls, and programmable lighting scenes provided both energy efficiency and flexible ambiance suited for different academic tasks. Electrical panels and communication rooms were distributed vertically in stacked risers, with horizontal branch wiring routed through raised floors or suspended trays to simplify future reconfiguration. Final commissioning included HVAC balancing, system testing, emergency power simulation, and fire alarm integration. With its vertical organization, modern utility core, and adaptive lab spaces, the FIT academic building reflects a technically intricate approach to education infrastructure, delivering high-performance functionality within the vertical constraints of its Manhattan environment. Perched high above the Colorado River, the construction of the Mike O'Callahan Pat Tillman Memorial Bridge required a level of structural precision and environmental coordination seldom encountered in highway infrastructure projects. Spanning nearly 900 feet across the Black Canyon, just downstream of the Hoover Dam, the project's location presented formidable challenges, including extreme elevation, rugged topography, high winds, and protected surroundings. The goal was to reroute U.S. Route 93 traffic off the Hoover Dam, necessitating a bypass bridge that could support heavy truckloads while enduring significant thermal and seismic forces. Foundation work began with the construction of vertical columns anchored into the canyon walls. These columns required deep rock sockets drilled into the solid bedrock on both the Nevada and Arizona sides. Blasting, rock bolting, and controlled excavation were used to establish working platforms and construct reinforced concrete footings. Once the columns were complete, temporary cable stays were strung across the canyon to support the next phase, the twin-rib concrete arch that would ultimately carry the bridge deck. This twin arch was built using a cantilever segmental method. Crews cast concrete segments outward from each canyon wall in balanced pairs, inching their way across the gap with the aid of a cable-supported highline system and traveling formwork. As each segment cured, post-tensioning tendons were tensioned internally to bind the structure and prevent shear or flexural failure. Each section was surveyed and adjusted using hydraulic jacks to maintain precise alignment as the arch legs advanced toward mid-span. Upon closure of the arch, deck construction commenced. Steel girders were lifted by cranes stationed on temporary towers and connected to the arch ribs through vertical spandrel columns. The bridge deck itself was a cast-in-place concrete slab, poured in sections with embedded rebar and expansion joints to accommodate thermal movement. Barrier rails, lighting systems, and crash protection were then installed along the deck edges. Wind and seismic design were paramount. The bridge incorporates tuned mass dampers and elastomeric bearings at key support points, allowing it to flex under dynamic loading without structural compromise. To ensure safety during construction, catwalks and harness points were anchored throughout the span, and workers operated under a highly regimented fall protection protocol. In the heart of downtown Miami, where the skyline rises in a collage of glass towers, 1000 Museum distinguishes itself not just by height, but by the extraordinary engineering involved in bringing its organic exoskeleton form to life. Long before any concrete was poured, the project demanded a fundamental rethinking of conventional tower design due to the decision to incorporate a curvilinear external structural system. The concept required that the building's primary structural support come from its exterior, a dramatic departure from the more common internal core and column system used in most residential high-rises. The foundation phase began with the installation of deep drilled shafts extending over 100 feet into Miami's sedimentary bedrock. These shafts were reinforced with heavy steel cages and trimly poured concrete to form a stable load path beneath the structure's core and its unique perimeter support zones. Above ground, the ground-level mat foundation included thousands of cubic yards of high-strength concrete, placed in continuous pours to avoid cold joints and ensure structural uniformity. The mat, several feet thick, had to be completed in multiple stages, each meticulously scheduled to coordinate pump trucks, concrete deliveries, and rebar placement. Skeleton became the central construction challenge. Rather than simple vertical columns, the perimeter frame was made up of sweeping biomorphic curves that branched and intertwined as they moved up the tower. This required a custom formwork system, fabricated off-site and assembled on-site in pieces, with tolerances often within a fraction of an inch. The forms had to be modified on a floor-by-floor basis due to the shifting geometries, and concrete placement was done in segments with continuous quality monitoring to prevent honeycombing or segregation within the curved shapes. Internal columns. Because the exoskeleton was exposed to the elements, its surface quality had to meet both structural and architectural criteria, requiring special attention during finishing, curing, and waterproofing. Routing HVAC, plumbing, and electrical lines through a tower with no conventional floor plate repetition required adaptive engineering and close collaboration among trades. A key component of the tower's innovation was the construction of a rooftop helipad, building loads at the highest elevation, along with wind load modeling to ensure rotor wash would not affect facade elements or roof equipment. Below the helipad, mechanical systems including chilled water plants and emergency generators were installed in hardened enclosures, isolated acoustically and vibrationally to avoid disturbing the building's luxury residential interiors. The glass curtain wall system was also a vital piece of the project. It had to be installed around the branching exoskeleton while maintaining weather tightness and minimizing air infiltration. Each panel was custom-shaped and tested for wind resistance, particularly given the building's exposure to hurricane-force conditions. Installation teams used specialized lifting rigs and sequencing plans to coordinate around the exoskeletal nodes, many of which intersected the glass modules in non-linear ways. Elevator and life safety systems, elevators, and pressurized stairwells. The building featured advanced smoke evacuation systems and a full backup power architecture integrated into the overall structural system.
The Sunrail Northern Extension to DeLand is a significant commuter rail infrastructure project expanding Central Florida's regional transportation network beyond its current northern terminus in DeBary. This extension involves upgrading an existing freight corridor owned by a Class 1 railroad to accommodate both passenger and freight operations. A complex endeavor requiring careful coordination, advanced civil engineering, and robust rail construction practices. Stretching approximately 12 miles, the extension is engineered to support high-frequency commuter trains while integrating with existing signaling, communications, and control systems already in operation along the rest of the Sunrail corridor. Construction began with comprehensive surveying and subsurface utility engineering to identify and avoid conflicts with buried infrastructure such as fiber optic lines, drainage culverts, and utilities paralleling the right-of-way. Track bed preparation commenced with clearing, grubbing, and regrading of the rail corridor to ensure proper drainage and subgrade stability. Where required, sub-ballast layers were improved or replaced using geotextiles and compacted granular material to ensure sufficient load-bearing capacity and long-term durability of the rail track structure. The single mainline track was upgraded using continuously welded rail, CWR, installed on concrete ties spaced and seated within a new bed of granite ballast. Rail sections were thermite welded in the field, followed by grinding and alignment to ensure smooth operation and minimize vibration. Ballast was placed in multiple lifts and tamped using automated machines that aligned and leveled the rail geometry to industry tolerances. Turnouts and crossovers were added strategically to allow passing operations and access to sidings, especially where freight and passenger train scheduling could potentially overlap. Bridge structures along the route, including culverts and overpasses, underwent inspection and, where necessary, rehabilitation to meet the higher loading standards required for passenger rail. Structural upgrades included concrete spall repair, bearing replacement, and in some cases, full superstructure reinforcement using steel plate bonding or carbon fiber wrap techniques. At-grade crossings were upgraded with new concrete panels, signal gates, and advanced train detection systems linked to positive train control (PTC) infrastructure to enhance safety and comply with federal mandates. The extension's new terminus at DeLand required the construction of a new passenger platform, parking area, and supporting infrastructure. The platform was built using precast concrete components, featuring tactile warning strips, lighting, canopies, and ADA-compliant ramps. Electrical and communications conduits were installed beneath the platform for future scalability. Adjacent facilities included a drop-off loop, pedestrian walkways, security systems, and stormwater management features designed to handle Florida's frequent rainfall. Signal system integration was a critical component of the project. Wayside signals, interlockings, and block detection systems were installed or modified along the route to provide seamless connectivity with the central dispatching system already managing Sunrail operations. Fiber optic cable was trenched along the corridor to provide real-time data transmission for PTC, train location monitoring, and emergency communication systems. Signal bungalows were prefabricated and installed on elevated concrete pads with backup power supplies to ensure system reliability during severe weather events. Construction operations were staged to minimize disruptions to existing freight traffic, requiring off-peak and nighttime work windows, flagging crews, and coordination with the freight operator to sequence activities without causing operational delays. Environmental protection measures were enforced throughout, including erosion control, wildlife protection plans, and careful management of work within wetlands and flood-prone areas. Permitting with state and federal transportation and environmental agencies was ongoing and comprehensive, reflecting the complexity of modifying an active rail corridor for dual-use functionality. Upon completion, the Sunrail Northern Extension to DeLand will provide vital transit connectivity to Volusia County, enhancing regional mobility while relieving highway congestion.
Stretching across the coastal plains of Kennedy County, Texas, the Penascal Wind Power Project showcases the application of large-scale renewable energy infrastructure in a challenging environment defined by soft soils, high humidity, and persistent coastal winds. The construction process begins with extensive site development, including topographical surveys, environmental assessments, and access road construction through otherwise undeveloped ranch land. These gravel roads must support the transport of extremely long turbine blades, tower sections, and nacelles, necessitating careful grading, compacted subbases, and wide turning radii for specialized transport vehicles. One of the primary engineering tasks in this project involves the foundation work for each wind turbine. The coastal soil profile, composed largely of silts and clays with varying moisture content, demands a foundation solution capable of resisting both vertical dead loads and dynamic overturning forces induced by wind. Each turbine foundation typically consists of a large circular reinforced concrete pad, often exceeding 50 feet in diameter and several feet thick, with a central pedestal rising above grade. The foundation is constructed after excavation, followed by rebar cage placement, anchor bolt installation, and a continuous concrete pour to ensure uniform curing and structural integrity. The turbine towers are delivered in multiple tubular steel sections, which are bolted together on-site using tensioned bolts and high-strength flanges. Erection is carried out using hydraulic or lattice boom cranes with lift capacities tailored to the height and mass of each tower segment. Each tower supports a nacelle, a housing unit for the generator, gearbox, and control electronics, which is lifted and mounted at heights reaching over 200 feet. Rotor assembly involves attaching 3 fiberglass reinforced blades to a central hub on the ground, then lifting the entire rotor assembly as a single unit and mating it with the nacelle. Electrical infrastructure includes the installation of underground medium voltage collection lines connecting each turbine to an on-site substation. These cables are buried in trenches with warning tape and sand bedding to prevent damage and ensure thermal dissipation. The substation steps up the voltage from around 34.5 kilovolts to transmission levels, often around 138 kilovolts, for integration into the regional grid. Control buildings house switchgear, protection relays, and SCADA systems that allow for remote monitoring and turbine control. Given the site's proximity to the Gulf of Mexico, the project incorporates several measures for corrosion resistance, including galvanization of structural steel, marine-grade coatings on exposed equipment, and sealed electrical enclosures. Turbines are fitted with lightning protection systems that channel electrical discharge safely to ground, a critical feature in a region prone to frequent thunderstorms. Operational testing involves synchronization of the turbines to the grid, blade pitch calibration, yaw system checks, and vibration analysis to ensure balanced rotation. Once commissioned, the Peñascal Wind Power Project contributes hundreds of megawatts of clean energy, capitalizing on the consistent wind resources of the South Texas coastline, while demonstrating advanced construction sequencing and logistical planning in renewable energy deployment. Revitalizing a historic waterfront facility for 21st-century industrial and renewable energy needs, the South Brooklyn Marine Terminal presents a unique case study in urban maritime infrastructure development. Situated on the edge of New York Harbor, the terminal's redevelopment hinges on heavy structural upgrades, environmental remediation, and the integration of new logistics capabilities tailored to offshore wind, bulk cargo, and intermodal freight handling. The initial phase of transformation involves evaluating the structural condition of the existing waterfront bulkheads, piers, and yard surfaces. Many of these elements date back several decades and suffer from deterioration due to tidal action, saltwater corrosion, and lack of continuous maintenance. Engineers perform sonar surveys and underwater inspections to assess the condition of timber piles, concrete caps, and steel sheet piles. Based on these findings, repair or full replacement strategies are selected. In many areas, new sheet pile walls are driven, reinforced with tiebacks and anchor rods connected to landward deadmen buried beneath newly placed compacted fill. Yard space across the terminal is reconstructed with load-bearing capacity in mind. The goal is to accommodate heavy crawler cranes, nacelle transporters, and oversized offshore wind turbine components. Subgrade stabilization may include dynamic compaction or deep soil mixing to reinforce the ground, followed by layered gravel bases and heavy-duty concrete or asphalt paving systems. Drainage systems are upgraded in parallel to manage stormwater runoff and prevent pooling on wide open surfaces that span several acres. Maritime access upgrades include dredging the berth to maintain appropriate depth for deep draft vessels. Clamshell dredging techniques remove sediment under environmental oversight, with turbidity curtains deployed to minimize dispersion. Dredged materials are tested and either treated or transported to designated disposal or reuse sites. New fendering systems and mooring bollards are installed along the quay walls to support ships delivering wind turbine towers, blades, and monopiles. The redevelopment integrates electrical and data infrastructure into the terminal footprint, essential for handling modern logistics and power-intensive operations. High-capacity substations, switchgear, and underground conduit networks are installed to support lighting, crane operations, and refrigerated containers. Fiber optic cabling ensures real-time coordination of equipment and inventory, and integrated control systems allow remote monitoring of yard activity and vessel movements. To accommodate rail connectivity, existing track alignments are restored and upgraded with new ballast, ties, and signal systems, enabling seamless intermodal transfer between ship, truck, and rail. Rail spurs are aligned to serve warehousing and storage zones efficiently, reducing turnaround time for large or awkward cargo. Heavy lift pads and roll-on to roll-off ramps are constructed to handle self-propelled modular transporters and specialized trailers. Finally, the terminal is configured to serve as a staging hub for offshore wind development. This includes designated laydown areas for wind turbine components, reinforced assembly zones, and barge loading platforms. Specialized lifting equipment, such as pedestal cranes or self-erecting gantries, is permanently installed or brought in on a project basis. The combination of marine access, ground capacity, and logistics integration positions the South Brooklyn Marine Terminal as a cornerstone of regional industrial infrastructure, engineered to support both current freight needs and the future of clean energy deployment. Breaking ground on the new Las Vegas Stadium project involves an immediate confrontation with both scale and site complexity. Before construction on any vertical elements could begin, civil crews undertook mass grading operations across a site encompassing dozens of acres situated near critical transport infrastructure. Excavation equipment worked around the clock to balance cut and fill volumes, and sediment control basins were installed to comply with regional stormwater regulations. Soil stabilization techniques, including lime treatment and compaction grouting, were applied in zones identified by geotechnical surveys as having potential for settlement. The structural skeleton of the stadium is expected to be a composite of reinforced concrete cores and structural steel framing, optimized to support a multi-tiered seating bowl and a retractable roof or canopy. Temporary shoring towers and formwork systems will be deployed to construct the poured-in-place vertical cores, which will house elevator banks, mechanical risers, and egress stairs. Once the cores reach adequate height, sequential steel erection will begin. This involves the staged installation of primary steel columns, roof trusses, and raker beams, using crawler cranes capable of operating at tight radii due to the constrained urban site. Simultaneously, the substructure below grade will include utility tunnels, equipment vaults, and mechanical rooms. These require waterproofing membranes, concrete admixtures for sulfate resistance, and cast-in-place slab systems with embedded sleeves for mechanical and electrical penetrations. Mechanical engineers will be installing a central chilled water plant, routing large-diameter piping through below-grade trenches and into elevated concourses through a system of vertical shafts and distribution headers. The stadium's envelope will likely employ high-performance glazing, custom aluminum rain screen panels, and photovoltaic-ready roof surfaces. These components will be supported by secondary steel framing and sealed using multiple air and moisture barrier systems. Installation of the facade will proceed from multiple elevations concurrently, using mast climbers and suspended scaffold systems. Wind bracing and lateral load transfer connections will be closely monitored during this phase using field weld inspections and survey control points. Interior fit-out will be driven by overlapping trades working in tiered zones, beginning in back-of-house service corridors and proceeding outward to premium suites, concessions, and seating areas. Audio-visual integration, including massive LED boards, arena-grade speaker systems, and real-time data infrastructure, will require extensive cable tray systems and climate-controlled control rooms. The new Las Vegas Stadium will ultimately stand as a hyper-engineered fusion of sports architecture and logistical orchestration, delivering a landmark capable of hosting international events and enhancing the city's already iconic skyline. Amid Florida's subtropical flatlands, the construction of Babcock Ranch Solar Town set out to prove that sustainable urban planning and utility-scale renewable energy could coexist in a master-planned community from the ground up. The project began with a rigorous environmental assessment of over 17,000 acres, ensuring that the development footprint would minimize disruption to existing wetlands and wildlife corridors. Extensive hydrological modeling was undertaken to manage the region's natural water flow patterns, with key areas set aside as conservation zones and integrated into the town's stormwater infrastructure. Once the primary civil grading was complete, roadways, utilities, and fiber optic communication lines were laid in tandem using a trench and backfill system coordinated through GPS-enabled machine guidance. Electrical distribution, unlike in most traditional developments, was built with solar generation as the core, not the supplement. Massive photovoltaic fields were constructed just outside the residential core, spanning hundreds of acres. The solar array used fixed tilt panels mounted on driven steel piles, with underground cabling channeling direct current electricity to inverters and step-up transformers before feeding into the regional grid. Residential construction throughout Babcock Ranch adhered to rigorous energy efficiency and wind resilience standards. Homes were built with insulated concrete form walls, impact-rated glazing, radiant barrier roof sheathing, and deep roof overhangs to mitigate solar gain. Roofing materials were chosen for their reflectivity and durability, including metal and tile products designed to exceed hurricane uplift requirements. Mechanical systems included high-SEER HVAC units, advanced dehumidification control, and smart thermostats integrated into home automation networks. What differentiated the town further was the full integration of microgrid technology. Battery storage facilities, housed in climate-controlled steel enclosures, provided grid balancing and backup capabilities. These systems ensured continuous power delivery even during grid disturbances and could island the town if necessary during extreme weather events. Switchgear, transformers, and substations were elevated on reinforced concrete pads with flood-proof enclosures and remote diagnostic sensors to prevent failure during high water levels. Public buildings and amenities, including schools, commercial centers, and community centers, were constructed using a design-build-delivery method to ensure consistency in green building standards and rapid delivery. All structures were wired for net metering, demand response control, and energy use feedback systems. Building envelopes featured continuous insulation, reflective membranes, and operable windows for cross-ventilation, where applicable passive cooling elements such as overhangs, louvers, and vegetative shading were incorporated into the architecture. Pedestrian infrastructure was planned ahead of vehicular design, with wide pathways, permeable paver systems, bioswales, and shade structures forming the connective tissue of the community. Stormwater is handled via a series of vegetated retention basins and interconnected canal systems, which serve dual purposes of flood mitigation and habitat support. Water and wastewater treatment systems were decentralized and included reclaim systems for irrigation, with smart meters installed throughout to promote conservation.
One Tampa is a high-rise residential tower under construction in downtown Tampa, Florida, set to become one of the tallest buildings on the city's skyline. This vertical development blends luxury condominium living with advanced structural engineering and urban construction logistics, standing as a significant example of high-density residential growth in a city undergoing rapid transformation. Its design calls for a slender tower profile supported by a heavily reinforced core and innovative construction methods to address both aesthetic goals and the complex engineering demands of building tall in a coastal, hurricane-prone environment. The project commenced with demolition and extensive site preparation in a tightly constrained urban setting. Excavation was limited due to surrounding structures and active utilities, requiring precision trenching and the use of engineered shoring systems to prevent soil collapse and protect adjacent property lines. Geotechnical analysis revealed a need for deep foundation systems, leading to the use of drilled shafts that extended well below the surface into competent limestone bedrock. Drilling rigs installed these caissons using slurry stabilization and steel reinforcing cages, followed by high-strength concrete pours to create vertical elements capable of supporting immense axial and lateral loads. With the foundation complete, the superstructure began with the central concrete core, which rises ahead of the surrounding floors. This jump-form core includes elevator shafts, stairwells, and service risers, and serves as the primary lateral load-resisting system. Around the core, post-tensioned concrete floor slabs are poured using flying formwork and edge protection systems, advancing at a pace of approximately one level every 5 to 7 days. Due to the tower's height and slender form, wind tunnel testing and computational fluid dynamics simulations were performed during design, resulting in the inclusion of outriggers and belt trusses at key levels to manage building sway and ensure occupant comfort under wind loading conditions. The building's facade consists of floor-to-ceiling glazing set within aluminum curtain wall panels engineered to resist hurricane-force wind and water intrusion. Each panel is installed from the outside using swing stages and sealed with silicone gaskets and pressure-equalized joints. Balconies are cantilevered from the slab edges and waterproofed using multi-layer membranes, with stainless steel railings and glass balustrades contributing to the tower's clean, modern appearance. Thermal performance and solar control are achieved through low emissivity coatings on all glazing. Mechanical, electrical, and plumbing systems are routed vertically through the core, with separate mechanical zones serving clusters of floors for optimal efficiency. high-efficiency HVAC units with variable refrigerant flow systems, energy recovery ventilators, and integrated building automation systems were installed to minimize energy use while maintaining indoor air quality. Electrical rooms and water risers are designed with redundancy, surge protection, and emergency power capabilities to maintain service continuity during outages. Interior construction is executed in phases as the structure rises. Once floors are enclosed, trades begin rough-in work for electrical, plumbing, and mechanical systems, followed by drywall, flooring, millwork, and finish carpentry. High-end finishes including stone countertops, engineered wood floors, designer lighting, and smart home integration systems are installed to meet luxury market expectations. Amenities such as a rooftop pool, fitness center, lounge areas, and business suites are distributed across podium and upper floors, each requiring specific structural and waterproofing provisions to support occupant loads, heavy equipment, and open water features. Construction logistics are tightly controlled due to the tower's location in a congested downtown area. A tower crane, material hoists, and just-in-time deliveries are coordinated to maintain workflow without obstructing public rights-of-way. A centralized construction management platform tracks progress, safety compliance, and material inventory in real time.
At the heart of downtown Austin, the Texas Capitol Complex Phase 2 represents a continuation of a multi-year development plan to expand and modernize state government infrastructure while respecting historical context. Construction activities begin with meticulous site logistics planning to accommodate the urban setting, including traffic control, pedestrian rerouting, and staging areas for heavy equipment within a dense government district. Selective demolition of outdated facilities and parking structures clears the way for excavation, utility relocation, and deep foundation work. Excavation reaches depths sufficient for multi-level underground parking and utility corridors. During this phase, crews deploy soil shoring systems using soldier piles and lagging or secant wall methods to ensure trench stability and protect adjacent buildings from settlement or vibration. Dewatering systems with sump pumps and well points are installed to maintain dry conditions during substructure construction. Concurrently, new utility infrastructure, chilled water lines, electric duct banks, and storm drainage systems are embedded in concrete-encased trenches. Structural concrete operations dominate the next phase, with mat foundations poured in multiple continuous placements to support new office towers. Tower cranes are erected early to facilitate vertical construction, hoisting rebar bundles, formwork panels, and precast components. Floor slabs are formed using a combination of post-tensioned and reinforced concrete techniques to optimize span lengths and reduce floor thickness. Core walls housing elevators, stairwells, and mechanical shafts are formed with slip-form systems to accelerate vertical progress while maintaining structural alignment. Above grade, architectural precast concrete panels are installed as part of the building envelope. These panels incorporate design motifs inspired by the adjacent Capitol and blend with the surrounding architectural aesthetic. Window systems include energy-efficient glazing and aluminum framing with integrated sunshades. Mechanical, electrical, and plumbing systems are integrated into each floor through overhead coordination with BIM modeling to avoid clashes and maximize efficiency in confined ceiling spaces. A key element of the project is the expansion of the Texas Capitol Mall, which introduces pedestrian green space atop underground parking decks. This requires careful waterproofing, drainage layering, and placement of structural soil to support landscaping elements. Trees, lighting, benches, and pathways are installed using detailed site plans to ensure ADA compliance and long-term durability. Interior finishes follow close behind structural completion, including raised flooring for cabling flexibility, modular wall systems, acoustic ceiling panels, and high-efficiency HVAC controls. Security systems, IT infrastructure, and life safety features are tested during commissioning. When completed, Phase 2 adds critical state office space, enhances connectivity through walkable corridors, and reinforces the ceremonial axis of the capital with modern construction methods and sustainable design. Transforming one of the busiest transportation hubs in North America demands not only technical expertise, but a delicate balance of preservation, modernization, and uninterrupted operations. The Penn Station redevelopment is an undertaking defined by both its architectural ambition and the intense logistical complexity of upgrading a live rail facility buried beneath one of the most congested city blocks in Manhattan. The effort to overhaul Penn Station begins with structural enhancements below grade. The existing concourses, tracks, and platforms operate under the weight of multiple buildings, including Madison Square Garden. Any changes to circulation pathways, vertical access points, or mechanical systems must be executed within strict spatial constraints, often involving night and weekend work windows when train frequency is lowest. Structural engineers rely on advanced 3D modeling and building information modeling systems to coordinate the dense layering of utilities, columns, HVAC ducts, fire suppression systems, and passenger circulation zones. One of the first technical priorities is the relocation and upgrading of aging mechanical and electrical infrastructure. High-voltage feeds, signal cabling, and ventilation shafts are rerouted through newly created utility corridors designed to accommodate future capacity and ease of maintenance. These corridors often require underpinning of adjacent foundations and careful bracing to prevent soil movement during excavation. In several locations, jet grouting and soil freezing methods are used to stabilize the ground before deep cuts are made beneath active rail beds. At platform level, modifications target the improvement of passenger flow, accessibility, and egress capacity. New elevator shafts and widened staircases are inserted through cutouts in the existing slab, reinforced with steel framing and temporary shoring during the coring process. The platforms themselves are resurfaced with high durability, slip-resistant materials, and edge warning strips compliant with current accessibility standards. New wayfinding signage, audio systems, and tactile floor indicators are integrated throughout to improve user navigation and safety. Above ground, the redevelopment includes the construction of new headhouse structures that serve as public-facing entry points to the station. These involve excavation for new foundation systems, often using drilled shafts or micropiles to thread through dense subterranean infrastructure. Superstructures are composed of steel framing and glass curtain wall systems, engineered for maximum daylight penetration and designed to bear dynamic loading from foot traffic and potential roof equipment such as photovoltaic arrays or emergency generators. To address capacity and improve commuter experience, mezzanine levels are expanded, requiring significant reconfiguration of load-bearing elements. New concourses are built with post-tensioned concrete slabs suspended over active track beds using a sequence of cast-in-place pours and pre-assembled rebar cages. Work zones are isolated using sound and dust barriers, with negative pressure ventilation systems ensuring air quality for both workers and travelers. All construction phases are coordinated with rail operators and emergency services. Detailed construction staging plans sequence deliveries, waste removal, and equipment installation into narrow time slots between train operations. Emergency egress routes are continually maintained and adjusted as interior spaces evolve. The redevelopment culminates in a completely modernized Penn Station environment, mechanically efficient, structurally sound, and navigable at volumes exceeding several 100,000 passengers per day, executed entirely while the existing system remains in full operation. Unlike many arenas that rise from open space, the T-Mobile Arena in Las Vegas was constructed on a tightly constrained urban site, requiring deep logistical planning before the first shovel hit the ground. The initial site preparation involved extensive utility relocation, as existing storm drains, water lines, and power conduits had to be rerouted to accommodate the building footprint and its supporting infrastructure. With minimal laydown space available, construction sequencing was planned in detail to ensure materials arrived just in time for installation. The structural system relied on a hybrid steel and concrete frame, A reinforced concrete core formed the arena's vertical circulation spine and housed elevator shafts, stairwells, and mechanical risers. Around this core, a complex array of steel columns, raker beams, and trusses supported the sweeping roof and cantilevered seating decks. The roof was particularly challenging as it required long-span trusses to bridge the open interior without intermediate columns, allowing unobstructed views from all seats. These trusses were lifted into place using synchronized crane lifts and were temporarily braced until lateral systems were completed. Within the bowl, precast concrete seating components were craned into position and set atop steel support members. The lower bowl was poured in place using cast-in-place concrete, allowing for integration of conduit chases and drainage systems directly into the slab. To ensure optimal acoustics, the interior envelope was lined with a combination of perforated metal panels and acoustic baffles, carefully arranged to diffuse sound energy and minimize echo. Mechanical systems were installed using vertical and horizontal distribution zones to maximize ceiling clearance and fan comfort. Chilled water plants, air handling units, and ductwork were located primarily above the event floor and distributed outward through high-level plenums. Special attention was given to integrating smoke control zones, emergency exhaust fans, and CO2 sensors into the overall HVAC design. Electrical systems featured redundant feeds, backup generators, and an extensive network of lighting control nodes to accommodate both performance and broadcast demands. The arena's exterior featured a curved facade made up of glass curtain wall, aluminum panels, and exposed structural elements. These were installed in phased sequences, using mast climbers and boom lifts to operate within the spatial limits of the surrounding development. Water infiltration protection was handled using rain screen design and perimeter sealant systems, ensuring long-term envelope integrity in the arid climate. Breaking ground on what is envisioned to become the largest retail and entertainment complex in North America, American Dream Miami is a mega project that combines commercial ambition with vast construction scale. The site, spanning several hundred acres in northwest Miami-Dade County, required extensive groundwork before vertical construction could even be considered. Initial site development involved substantial clearing and grubbing of existing vegetation, followed by the removal of unsuitable soils and replacement with engineered fill. Soil compaction and moisture conditioning were conducted systematically, zone by zone, to meet strict geotechnical specifications given the project's susceptibility to high water tables and the underlying karst limestone. Stormwater management was one of the most critical challenges from the onset. Crews installed a comprehensive drainage network composed of perforated HDPE pipes, catch basins, and retention ponds to control runoff during South Florida's intense rainfall events. Because of the site's proximity to sensitive wetlands, strict environmental controls had to be maintained throughout construction. Silt fences, turbidity barriers, and regular environmental monitoring were deployed to ensure compliance with state and federal mandates. The primary structure of the complex comprises a combination of reinforced concrete and structural steel, chosen based on load distribution needs and span requirements. While concrete forms the foundation mat and shear walls, wide-span areas such as the indoor ski slope, water park enclosure, and retail atriums utilize steel framing with long-span trusses and moment connections. The ski slope, one of the central engineering feats, requires a climate-controlled interior envelope over several hundred feet long, with complex thermal insulation and vapor barrier systems. The structural shell is thermally isolated from the surrounding environment, using insulated metal panels and a controlled HVAC system designed to maintain sub-freezing temperatures in a tropical climate. Mechanical, electrical, and plumbing coordination was a substantial portion of the build process, with extensive BIM modeling used to resolve spatial conflicts in densely packed service corridors. Chilled water systems, electrical bus ducts, and fire sprinkler mains all had to be routed through the superstructure without interfering with visitor circulation, escalator shafts, or themed architecture. Substations and cooling towers were strategically located in peripheral service yards to reduce ambient noise and heat near visitor zones. Specialized foundations were needed in areas designated for amusement rides, where dynamic loads exceeded standard building tolerances. Engineers embedded deep auger cast piles beneath the footings to transfer those loads to stable substrata. Vibration isolation systems and seismic expansion joints were installed at strategic intervals to ensure ride safety and structural resilience. Exterior construction involved a layered system of weather-resistant barriers, rain screen cladding, and themed facades that change appearance depending on the function of each zone. Materials ranged from precast concrete panels to architectural glass and high-pressure laminates. For the water park roof, translucent ETFE panels were chosen to allow natural light while minimizing solar heat gain, thereby enhancing energy efficiency.
Riverfront Plaza in Jacksonville is a transformative redevelopment project situated along the St. Johns River in the heart of downtown. Formerly the site of the Jacksonville Landing, this new urban park and civic space is designed to integrate green infrastructure, community gathering areas, public art installations, and a landmark architectural feature into one continuous waterfront environment. The construction process for Riverfront Plaza is a blend of civil, landscape, structural, and utility engineering disciplines working together to reshape an iconic portion of the city's shoreline while addressing flood control, stormwater management, and long-term resilience. Demolition of the former structures marked the beginning of the project, involving selective deconstruction and recycling of building materials to minimize environmental impact. Once the site was cleared, geotechnical studies identified bearing capacity, soil composition, and potential contaminants from decades of prior development. Remediation work included soil stabilization, compaction, and in some areas, the replacement of substandard fill with engineered material to support hardscaping and load-bearing features. Perimeter erosion control and sediment fencing were installed to protect the adjacent river during earth-moving activities. One of the critical technical challenges was the elevation management of the plaza to accommodate both pedestrian use and flood mitigation. The design incorporates terraced levels and bioswales that direct stormwater away from heavily trafficked zones and toward vegetated catchment areas. Drainage infrastructure beneath the surface includes a network of perforated pipes, underdrains, and retention basins that allow water to percolate through soil media layers, reducing runoff and filtering pollutants before water reaches the river. Hardscape elements such as pathways, amphitheater seating, and event lawns are supported by concrete slabs and modular paver systems laid atop compacted subbases with integrated utility conduits for lighting, irrigation, and power supply. The installation of lighting poles, surveillance equipment, and public Wi-Fi access points was coordinated to minimize trenching and disturbance of landscaped zones. Foundation work for the signature art installation or vertical landmark structure included drilled concrete piers and anchorage systems capable of resisting wind and uplift forces, especially critical given the site's exposure to hurricanes and river breezes. The landscaping phase utilized native and adaptive plant species to create a biodiverse environment that requires minimal irrigation. Soil amendments, root barriers, and subsurface anchoring systems were used to ensure healthy tree growth while preventing root encroachment into hardscape zones. Installation of urban furniture, shade structures, and wayfinding signage followed, executed with precise alignment and coordination to maintain accessibility and sightlines throughout the plaza. Simultaneously, riverfront bulkhead repairs and reinforcements were conducted to address long-term shoreline erosion. These efforts included driving new sheet piles and installing riprap where necessary to stabilize the bank while integrating it visually with the park's design. All construction activities required ongoing coordination with municipal agencies, local businesses, and public stakeholders to manage access, maintain safety, and adhere to schedule constraints.
The Bay City Green Hydrogen Plant is an advanced industrial facility designed to produce hydrogen using electrolysis powered by renewable energy sources, primarily solar and wind. Situated in proximity to both energy supply corridors and industrial hydrogen demand centers, the project begins with extensive land development, which includes grading, drainage design, and geotechnical stabilization to support heavy equipment loads and ensure safe operation under varying environmental conditions. Electrical grounding systems are embedded in the foundational layout to protect sensitive electrolysis components from surges and lightning. Once the site is cleared and compacted, construction of the primary electrolysis units begins. These systems, typically using proton exchange membrane or alkaline electrolyzer stacks, require a precise mechanical and electrical assembly environment. Prefabricated skid-mounted modules are delivered to the site, each containing electrolyzer cells, transformers, rectifiers, and water purification units. These modules are set on reinforced concrete pads with embedded anchor bolts to withstand thermal cycling and mechanical vibrations. Deionized water feed systems are installed, incorporating reverse osmosis and filtration units to ensure electrolyte purity, which is critical for electrolyzer efficiency and longevity. Adjacent to the electrolyzers, a high-voltage substation is constructed to interface with renewable energy sources. This substation steps down incoming electricity from transmission voltages to operational levels suitable for the direct current systems feeding the electrolysis stacks. Power distribution infrastructure includes underground cable trays, switchgear enclosures, and load centers with automated fault detection. Battery energy storage systems are often co-located to buffer intermittent generation from renewables, smoothing out power supply fluctuations to maintain consistent hydrogen output. Hydrogen produced on-site is directed through stainless steel piping systems to compression units where it is pressurized for storage or distribution. These compressors are housed within sound-attenuated enclosures to meet regulatory noise limits and are equipped with redundant safety valves and blowdown stacks. Storage vessels, typically cylindrical tanks rated for several hundred bar, are constructed using high-strength carbon steel alloys and are fitted with pressure and temperature monitoring instrumentation. A control center oversees plant operations via a distributed control system that integrates sensors, flow meters, and programmable logic controllers. Real-time data acquisition enables operators to optimize electrolysis efficiency and respond to any anomalies. The plant also incorporates emergency shutdown systems, gas leak detection, and fire suppression equipment to meet industrial safety standards. Upon completion, commissioning involves a phased startup of each system, pressure testing of gas lines, calibration of instrumentation, and validation of control logic before the plant is cleared for continuous green hydrogen production. Beneath the dense urban landscape of the northeastern United States, the Gateway Program's Hudson River Tunnel project emerges as one of the most intricate and vital rail infrastructure undertakings in the country. At its core, the tunnel is designed to bolster the heavily trafficked Northeast Corridor by constructing new twin tunnels beneath the Hudson River, providing a long overdue supplement to the existing pair of century-old tunnels that currently operate at near full capacity. Construction begins with extensive geotechnical investigations to map out the subsurface conditions beneath both the river and the surrounding urban areas. This involves drilling boreholes, performing seismic refraction surveys, and collecting core samples to evaluate the composition and stability of the underlying rock and sediment. Because the Hudson River bed consists largely of soft silt and clay atop layers of glacial till and bedrock, tunnel boring machines must be selected and calibrated with these highly variable ground conditions in mind. Launching the tunnel drives requires the excavation of deep approach shafts on both the New Jersey and Manhattan sides. These shafts provide access for tunnel boring machines and serve as critical logistical hubs for removing excavated material and bringing in precast concrete segments. Due to spatial constraints, particularly on the Manhattan side, where active rail lines and dense development restrict movement, all construction staging and materials delivery must be meticulously coordinated to avoid disruptions to existing rail operations. Tunnel boring machines used in this project are earth pressure balance types, capable of maintaining face stability while simultaneously installing the tunnel lining. These machines advance gradually, segment by segment, using a rotating cutter head to excavate material, while hydraulically driven erector arms install curved precast concrete segments into a ring formation. These segments are tightly bolted and gasketed to form a watertight structure capable of resisting the intense pressures from both the river and surrounding soil. As the tunnel progresses beneath the river, constant monitoring systems are deployed to detect ground settlement, machine performance, and water ingress. These systems ensure that any anomaly is detected and mitigated before it can threaten the structural integrity of the tunnel or impact above-ground infrastructure. Ventilation and safety systems are gradually installed behind the boring machines, including emergency egress pathways, fire suppression conduits, and future cabling ducts for power and communications. Upon completion of boring, the tunnel interiors must be outfitted with track systems, traction power supply, signaling equipment, and drainage systems. Specialized crews install continuous welded rail on concrete ties, ensuring smooth and safe high-speed travel. The power infrastructure includes overhead catenary lines supported by rigid cantilever arms, interfaced with substations to provide consistent electrical feed to passing trains. Advanced signal systems, designed for positive train control integration, are installed to meet current federal safety standards and accommodate future automation capabilities. When a bridge reaches the end of its useful life, replacement becomes not just a matter of modernization, but of safety and resilience. This principle guided the reconstruction of the Tiugniauga River Replacement Bridge, a project set in motion to restore reliable vehicular connectivity across the river while improving structural standards and accommodating future load demands. The existing bridge, after decades of service, exhibited wear typical of aging steel and concrete structures exposed to freeze-thaw cycles, road salt, and high water events. At the outset of the MSG Sphere's construction in Las Vegas, the most immediate challenge was establishing a foundation capable of supporting a structure unlike anything previously built. The sphere's extreme diameter, spanning over 500 feet, and height exceeding 300 feet, necessitated a ring of deep foundation caissons. These caissons, drilled dozens of feet into the caliche-laden desert subsoil, provided load-bearing support for the concrete mat foundation that would carry the entire dome. Crews installed dense rebar cages and tremi-poured concrete in segments, ensuring continuous integrity under the enormous compressive and lateral loads. The frame of the sphere was formed using a hybrid structural system combining concrete cores with an extensive steel diagrid shell. The steel members, many of them curved and custom fabricated, were craned into place with extreme precision. Each joint had to accommodate subtle geometric variances in the spherical curvature, requiring extensive use of laser surveying and point cloud modeling during assembly. The use of node connectors, each one custom engineered, allowed thousands of steel segments to interlock into a stable geodesic structure. Work progressed concentrically, rising from the base upwards, forming a self-supporting lattice that grew in stages toward closure at the apex. Internally, the complexity intensified. The sphere's defining feature, its fully immersive LED display surface, required a compound curved interior supported by catwalks and rigging systems hidden behind the paneling. This interior surface included more than 100,000 square feet of high-resolution LED panels. Engineers had to account for thermal expansion, cable routing, and precise angles of incidence for projection mapping and acoustics. To achieve truly immersive sound, an advanced beam-forming audio system was suspended behind acoustic mesh panels, calibrated to direct audio precisely to each seat using an array of over 100,000 speakers and transducers. Externally, the sphere's envelope was sheathed in an exoskeleton clad with LED modules designed for all-weather performance. These panels were mounted using modular aluminum frames anchored directly to the diagrid steel. Wind loading, thermal cycling, and desert dust all influenced the choice of materials and mounting systems. Throughout the build, access was achieved with a mix of suspended scaffolds, articulating lifts, and perimeter ring cranes. Construction sequencing had to account for limited laydown space and active coordination with surrounding infrastructure. With the Las Vegas Strip nearby, noise restrictions, traffic control, and night work all shaped how the project advanced. The MSG Sphere stands as a demonstration of digital architecture converging with structural audacity, where immersive entertainment dictated the blueprint from foundation to facade.
The reconstruction of Tyndall Air Force Base in Panama City, Florida, is one of the largest and most advanced military installation rebuilds in modern U.S. history, driven by the extensive damage caused by Hurricane Michael in 2018. This reconstruction effort represents a long-term, multi-phase infrastructure and facilities redevelopment plan centered on resilience, mission readiness, and advanced technology integration. Designed to support next-generation fighter aircraft like the F-35, the effort required a complete reimagining of the base's built environment, including structural systems, utilities, flight line infrastructure, and storm-hardened facilities. Initial efforts began with damage assessment, site clearance, and debris removal, carried out by joint military and civilian engineering teams. Buildings deemed unsalvageable were demolished in a controlled sequence, with materials sorted for recycling or disposal. Simultaneously, civil engineers conducted a comprehensive geotechnical and hydrological survey across the installation to inform the design of new structures, utility corridors, and stormwater management systems. Much of the soil had to be reconditioned or replaced due to saturation and compaction caused by the storm, requiring stabilization techniques such as lime treatment, compaction grouting, and subgrade reinforcement using geosynthetics. The master plan for the rebuilt base incorporated distributed utilities, redundant systems, and hardened structures. Electrical infrastructure was placed underground where feasible to reduce vulnerability to wind and debris. Water, sanitary sewer, and communications networks were reconstructed using corrosion-resistant materials, with looped layouts allowing for continuous service during partial outages. Substations, lift stations, and control buildings were housed in wind and flood-resistant enclosures built to withstand Category 5 hurricane conditions. Vertical construction emphasized hardened concrete and steel structures with progressive collapse resistance, blast resistance, and full compliance with unified facilities criteria. Aircraft hangars were designed with clear spans exceeding 200 feet, supported by structural steel frames and braced bays. Roof assemblies used standing seam metal over insulated decking systems, anchored with high-load mechanical fasteners and uplift rated to survive extreme wind events. Maintenance bays, munitions storage, and logistics centers were outfitted with reinforced concrete walls and storm-rated doors, ensuring continuity of operations during adverse conditions. Flight line reconstruction involved complete resurfacing of taxiways and aprons, the addition of new lighting systems, jet blast deflectors, and improved stormwater drainage. Concrete pavements were installed over stabilized subbases, with expansion joints and reinforced panels capable of supporting repeated F-35 operations. Navigational aids and radar systems were relocated and shielded for increased survivability, while air traffic control towers were rebuilt with hardened glazing and backup power systems. Administrative and residential facilities were constructed with modular, energy-efficient designs, incorporating passive solar features, high-performance insulation, and low-impact development strategies. Barracks, dining facilities, and command buildings included progressive energy systems like solar photovoltaic arrays, advanced building management systems, and high-efficiency HVAC systems. Smart base technology was embedded throughout, including automated access control, video surveillance, and integrated cybersecurity protocols governing building automation and mission-critical systems. Logistics for the reconstruction were coordinated under a hub-and-spoke model, with central material laydown yards, controlled access zones, and precision delivery scheduling to manage the flow of construction equipment, materials, and personnel. Construction was executed in overlapping phases to allow ongoing base operations, requiring strict safety and coordination protocols. Federal, state, and local permitting was streamlined under mission priority guidelines, with environmental compliance maintained through on-site inspectors and adaptive sedimentation control measures.
Towering above one of the busiest highway corridors in North Texas, the High-5 interchange in Dallas stands as a hallmark of multi-level interchange engineering. Built to replace a congested cloverleaf interchange where U.S. Highway 75 intersects with Interstate 635, the project required innovative design and construction techniques to manage complex traffic patterns while maintaining continuous vehicle flow through one of the region's primary transportation arteries. Initial phases began with detailed traffic modeling, utility mapping, and soil investigations to support the five-tiered structure's foundation. Given the depth of the lower roadways and the height of the upper ramps, foundation construction included the use of deep drilled shafts extending over 100 feet into the ground. These shafts were reinforced with heavy rebar cages and cast with high-strength concrete to support the significant vertical and lateral loads imposed by tall piers and long-span bridge decks. The interchange's construction was sequenced using a segmental approach, allowing multiple elevated ramps to be built concurrently with minimal interference to active lanes below. Crews used massive cranes to place precast concrete segments and steel girders at heights reaching over 120 feet. False work towers and temporary supports were utilized extensively to hold bridge components in place until post-tensioning systems were installed to lock the segments into structural integrity. Each level of the interchange demanded precise vertical and horizontal alignment, especially in the curved flyover ramps that must safely accommodate high-speed traffic. Bridge decks were formed using steel-reinforced concrete with epoxy-coated rebar to enhance corrosion resistance, an essential consideration in a structure exposed to both descent salts and Texas heat. Expansion joints, drainage inlets, and safety barriers were integrated during deck placement to ensure long-term durability and operational safety. Utility coordination was a major undertaking as numerous fiber optic lines, water mains, and gas lines crossed the construction zone. Relocation efforts required directional drilling, jack and bore methods, and trench excavation under tightly managed shutdown windows. In parallel, intelligent transportation systems were embedded, including dynamic signage, surveillance cameras, and real-time traffic sensors networked to regional control centers. Lighting, landscaping, and architectural detailing followed structural completion, contributing to the interchange's distinct urban identity. At full build-out, the High-5 interchange improved traffic capacity, reduced weaving conflicts, and significantly enhanced mobility for both regional and local drivers, all achieved through precise civil engineering, rigorous construction phasing, and innovative use of vertical space. Laying an undersea transmission line is an operation that combines offshore engineering, marine geology, and high-voltage electrical infrastructure into a single continuous challenge. In the case of Empire Wind 1, the transmission system forms the backbone that delivers power from the offshore wind turbines to the onshore grid, spanning seabed, shoreline, and terrestrial corridors. The design and construction of this export cable involve multiple phases, each requiring distinct sets of equipment, expertise, and environmental management. The subsea cable installation begins with a detailed seabed survey. Hydrographic mapping, magnetometer readings, and geotechnical bore samples inform the alignment of the export route. The goal is to avoid boulders, shipwrecks, ecologically sensitive areas, and existing infrastructure like pipelines or fiber optic cables. Based on these findings, the route is finalized and cable protection measures are engineered, including burial depth profiles and potential use of rock berms or articulated concrete mattresses in harder substrates. Cable manufacturing is done well in advance, with the high-voltage alternating current cables fabricated in long, continuous segments. Each cable is composed of a central conductor, typically copper or aluminum, surrounded by layers of insulation, semiconducting sheaths, metallic armor, and external jackets. These cables are spooled onto massive turntables and loaded onto cable-laying vessels equipped with dynamic positioning systems to maintain exact alignment during installation. Prior to laying, a pre-trenching or plowing operation prepares the seabed. A remotely operated plow or jetting tool creates a narrow trench into which the cable is laid in a single pass. The cable-laying vessel then feeds the cable from its deck through a guide chute while maintaining precise tension and layback control. In areas where burial is not possible, post-lay protection using rock placement or concrete mats is deployed to prevent damage from anchors or trawling. At the landfall interface, a horizontal directional drilling method is used to bring the cable on shore without disturbing the shoreline or sensitive coastal environments. A borehole is drilled from an onshore pit out to the nearshore seabed, where a receiving pit or offshore transition joint bay is located. A duct is installed through this borehole, and the cable is pulled through using a winch system, creating a continuous sealed connection from sea to land. Onshore, the cable transitions from marine-grade insulation to terrestrial specifications at a cable transition joint housed in a secure underground vault. From there, the cable continues along a buried conduit route to the onshore substation, which is often newly constructed or significantly expanded to handle the incoming capacity. The substation includes transformers, switchgear, reactive compensation equipment, and grid interconnection systems. High-voltage transformers step the transmission voltage to a grid-compatible level, while harmonic filters and reactive power equipment stabilize voltage and frequency. Commissioning of the transmission system includes extensive high-voltage testing, thermal modeling, and live energization sequences. Protective relays and fault detection systems are calibrated to ensure the system can isolate any short circuits or overloads. Once operational, the Empire Wind 1 transmission line functions as the vital conduit converting offshore wind energy into urban-scale electricity supply, delivering clean energy while showcasing the precision and coordination demanded by subsea electrical engineering. Construction of the Brightline West high-speed rail begins not with rails, but with an extensive corridor preparation effort stretching along the Interstate 15 right-of-way between Southern California and Las Vegas. The alignment was selected to leverage existing transportation corridors, minimizing environmental impact while reducing the need for new land acquisition. Survey teams marked out the route using GPS-based geolocation, after which clearing and grubbing crews removed desert vegetation and leveled the alignment in preparation for subgrade construction. Due to varying soil conditions, crews implemented soil stabilization techniques such as cement treatment and moisture conditioning to achieve the compaction required for long-term settlement resistance. The rail substructure comprises several layers, beginning with compacted subgrade, followed by engineered fill, and a layer of ballast in zones where traditional track is used. However, in high-speed segments, especially those reaching over 180 miles per hour, a concrete slab track system will be utilized. This involves pouring continuous reinforced concrete slabs with expansion joints and embedded fasteners designed to hold the rail in place with millimeter-level precision. These slabs are set atop geotextile membranes and drainage systems to prevent water infiltration and thermal heave. Bridges and viaducts form a critical part of the project, particularly where the line crosses over existing roadways or environmentally sensitive terrain. Precast concrete girders are transported via specialized haulers and lifted using high-capacity gantry cranes. Abutments and piers are constructed using drilled shaft foundations, with rebar cages tied on site and lowered into the shafts before concrete placement. In seismic zones, isolators and energy-dissipating devices are installed to ensure structural resilience during earthquake events. Catenary systems for electric power delivery require the installation of overhead contact system, poles spaced at precise intervals along the corridor. These poles are anchored in concrete footings and support tensioned copper conductors delivering 25 kilovolts AC. Power substations are built at strategic intervals, converting utility-scale electricity to the necessary specifications for the trains and feeding the system through switchgear and protection circuits. Stations are designed as intermodal hubs, integrating ticketing systems, security screening, vertical circulation, and baggage handling. Platform edge doors, vibration damping structural slabs, and acoustically treated canopies are incorporated to ensure comfort and safety at high-speed boarding conditions. All systems are tied into a centralized traffic control center that uses fiber optic networks and redundant data links for command, monitoring, and dispatch. Brightline West aims to redefine regional travel by delivering a fully electric, high-capacity corridor built with exacting civil and systems integration standards tailored for American infrastructure. Starting from its immense foundation work, the construction of Panorama Tower in Miami was an engineering endeavor that pushed the limits of vertical urban development in South Florida. The site preparation required the excavation of a deep foundation mat nearly 10 feet thick, which would ultimately support the enormous structural loads of what became the tallest building in the state. The tower's foundation system relied on a network of auger cast piles extending more than 100 feet below grade, drilled through soft coastal sediments into underlying limestone strata. A high-strength concrete pour of over 13,000 cubic yards was executed in a continuous operation lasting more than 24 hours, involving dozens of concrete trucks in a carefully choreographed rotation. Once vertical construction began, the superstructure rose rapidly using a cast-in-place concrete core system. The central shear walls formed the backbone of the tower, housing elevator shafts, stairwells, and mechanical risers. Surrounding this core, post-tensioned concrete slabs and columns were poured in a cycle of roughly one floor every 4 to 5 days. To maintain this pace, formwork systems were mounted on self-climbing hydraulic jacks, and a just-in-time delivery system kept materials flowing without congesting the tight urban staging area. The building's mix of residential, commercial, and hotel uses demanded varied floor layouts and load-bearing considerations. Transfer girders, some spanning over 30 feet, were integrated at podium levels to redistribute structural loads around open lobby and amenity spaces. These massive concrete beams required temporary shoring towers and custom formwork assemblies, built and dismantled as the structure progressed upward. Mechanical systems throughout the tower had to account for vertical reach, energy efficiency, and hurricane resilience. Multiple chiller plants were stacked vertically at mechanical floors to optimize thermal load distribution. Water pressure zones were engineered using variable speed booster pump systems and brake tanks to maintain consistent pressure throughout the more than 80 stories. The electrical system incorporated dual feeds and emergency backup generation housed on elevated floors to avoid flooding risk. Vertical duct shafts were carefully coordinated with structural elements using 3D modeling tools to prevent clashes. The curtain wall system was engineered for high impact resistance and thermal performance. Each panel included laminated glass, extruded aluminum frames with thermal brakes, and anchoring systems rated for over 170 miles per hour wind loads. Installation occurred using mast climbers and swing stages, starting from the mid-tower levels and working both upward and downward. Balconies were constructed with cantilevered concrete slabs and glass railings carefully sloped to direct water runoff away from the facade. Elevator logistics were especially critical in such a tall structure. High-speed gearless traction elevators with destination dispatch were installed to minimize wait times, and reinforced machine rooms were positioned at intervals to house motors and control equipment. Fire protection systems included pressurized stairwells, zoned sprinkler systems, and smoke control fans, all tied into a centralized life safety command center.
Pendry Residences. Tampa is a luxury high-rise development currently under construction along Tampa's waterfront, representing a fusion of advanced residential tower engineering, mixed-use construction techniques, and coastal urban design. Rising prominently above the Riverwalk, this structure is planned as a combination of high-end condominiums and a luxury hotel, requiring a complex interplay between structural systems, vertical transportation logistics, and premium interior build-outs tailored to discerning occupants. The initial stages of construction began with detailed geotechnical studies to assess the subsurface conditions characteristic of Tampa's reclaimed and water-adjacent lands. Due to the potential for soft soils and high groundwater levels, the design necessitated deep foundations. Contractors deployed large rotary drilling rigs and pile-driving barges to install auger-cast piles or drilled shafts, ensuring that each foundation element penetrated down to load-bearing strata. Dewatering systems were concurrently operated to keep the excavation areas dry during the pile cap and mat foundation work. Sheet piling and temporary shoring systems enclosed the below-grade sections, allowing crews to safely form and pour the concrete base structures, including utility trenches and basement-level mechanical rooms. Once the substructure was complete, the superstructure advanced vertically using high-strength post-tension concrete slabs poured floor by floor in a sequential schedule coordinated with vertical formwork and scaffolding systems. The core of the building, housing elevators and stairwells, rose ahead of the floor plates using a jump-form system that provided both speed and rigidity. Because of the dual-use nature of the tower, serving both hotel guests and permanent residents, the mechanical and electrical design was bifurcated into separate but overlapping systems, each with isolated metering, HVAC zones, and fire suppression networks. Fireproofing, soundproofing, and vibration control systems were embedded throughout the vertical risers to isolate residential spaces from hotel operations. The building's facade was constructed using a curtain wall system comprised of high-performance, hurricane-rated glazing units and insulated aluminum frames. These were prefabricated off-site and installed via tower cranes and swing stages, allowing for a quick enclosure to facilitate interior trades. Inside, the fit-out involved bespoke finishes including imported stone, hardwood flooring, and integrated smart controls for lighting, climate, and security. High ceilings, expansive balconies, and floor-to-ceiling glass presented coordination challenges, especially regarding thermal insulation and waterproofing at slab edges and window junctions. Elevator cores were outfitted with high-speed lifts, some designated as private residential access with keycard control. Amenities such as rooftop pools, spas, lounges, and fitness centers required structural reinforcement in the upper levels to support the added loads from water tanks, equipment, and occupancy. These spaces were waterproofed with multi-layer membranes and tested for leakage prior to finish installation. Mechanical penthouses and rooftop equipment were enclosed in acoustically treated screen walls to reduce impact on nearby buildings. The logistical demands of building in downtown Tampa required precise coordination for crane positioning, material staging, and just-in-time delivery, with special consideration for pedestrian safety and traffic flow around the active Riverwalk. Permitting and inspections were rigorous due to the project's scale and waterfront proximity, involving compliance with city zoning, FEMA floodplain guidelines, and wind load requirements specific to Florida's Gulf Coast.
Rising prominently over the Corpus Christi Ship Channel, the Harbor Bridge Replacement Project represents a transformative upgrade to the region's transportation and maritime infrastructure. The effort to construct the new bridge begins with significant preparatory work, including clearing, grading, and establishing access roads for heavy machinery. Crews undertake extensive geotechnical surveys to design deep foundation systems that can safely support the towering cable-stayed structure in a coastal environment prone to high winds, corrosive salt air, and variable soil conditions. The core of the construction involves the installation of massive drilled shaft foundations. These are created using rotary rigs that bore deep into the substrata, often through layers of clay, sand, and limestone. Reinforcing steel cages are then lowered into the shafts and encased in concrete to form durable vertical supports. Given the location over navigable waters, temporary work platforms and marine barges are mobilized to provide access and material staging for overwater operations. The centerpiece of the bridge consists of two towering pylons that anchor the cable-stayed design. These pylons are constructed incrementally using a climbing formwork system that allows each concrete lift to cure before the next section is poured. Precision alignment is essential as the pylons must remain perfectly vertical over hundreds of feet of elevation. Once the pylons reach their full height, installation of the stay cables begins. These high-tension steel cables are anchored at the pylons and radiate outward in a fan-like array to support precast bridge deck segments. Deck segments are installed using a balanced cantilever method, where sections are added symmetrically from both sides of the pylon to maintain structural equilibrium. Each segment is carefully aligned and post-tensioned into place, forming the long-span roadway over the ship channel. Throughout this process, real-time structural health monitoring systems are employed to measure stress, displacement, and vibration to ensure safety and integrity during construction. The bridge approaches are constructed concurrently, involving the erection of elevated spans supported by precast concrete girders and pier caps. These components are assembled using cranes and falsework, followed by placement of the riding surface and expansion joints. The project also includes roadway realignments, upgraded interchanges, and the integration of pedestrian and bike paths to enhance multimodal accessibility. Upon completion, extensive commissioning activities verify all structural, electrical, and drainage systems. The new harbor bridge will provide significantly improved clearance for maritime traffic, greater traffic capacity for vehicles, and enhanced resilience against hurricanes and seismic events, marking a new chapter in regional infrastructure advancement. The replacement process began with a comprehensive assessment of hydrological patterns along the Tugneoga River. Engineers conducted hydraulic modeling to determine the appropriate bridge height and span length that could withstand a 100-year flood event. River scour, which had contributed to undermining the older abutments, necessitated special attention in the design phase. To counteract this, deep foundation systems such as driven steel piles and reinforced concrete caissons were specified to anchor the substructure well below the scour depth. Construction sequencing had to be carefully planned to maintain traffic flow. In many such cases, a temporary detour structure or a stage construction method is adopted. Here, stage construction allowed half of the bridge to be built while traffic continued on the remaining half, supported by temporary shoring and reinforced decking. This minimized disruptions to local communities and commercial routes. Demolition of the old bridge structure required systematic deconstruction, starting with deck removal followed by segmental dismantling of girders and piers. Environmental controls were deployed to prevent debris from entering the river, including floating turbidity curtains and debris nets. Once cleared, work commenced on the new foundations, which included cofferdams constructed from interlocking sheet piles to isolate work zones from the water and create a dry workspace for excavation and concrete placement. The superstructure was designed as a multi-span steel girder bridge with composite concrete decking. High-performance weathering steel was chosen for the girders to reduce long-term maintenance by forming a protective oxide layer. The concrete deck was poured over galvanized stay-in-place forms, with integral shear studs to create a composite action between the steel girders and the concrete slab. Expansion joints and neoprene bearing pads were incorporated to accommodate thermal movement and live load deflection. The bridge rails and parapets were upgraded to meet current crashworthiness standards, employing reinforced concrete barriers with a steel rail on top. Drainage features were integrated into the deck design to channel water away efficiently, reducing the risk of icing in colder months. Roadway approaches were reconstructed with improved alignment and transition zones, incorporating guardrails, pavement striping, and signage to enhance driver safety. Throughout the project, geotechnical instrumentation monitored settlement and lateral movement, ensuring foundation integrity as loads transferred from the superstructure. Final inspections included load testing, visual surveys, and non-destructive evaluation methods such as ground-penetrating radar and ultrasonic testing of welds. Upon opening, the new Tugneoga River Replacement Bridge represented not just a physical crossing, but a renewed commitment to infrastructure longevity and regional mobility, crafted through rigorous engineering and carefully managed construction logistics. Shifting focus to one of the most significant sports construction projects in recent American history, Allegiant Stadium in Las Vegas began with an enormous excavation effort to prepare the site just west of the Strip. The soil conditions required pre-treatment due to high water tables and loose granular fill. To stabilize the subgrade, contractors used deep soil mixing and installed wick drains to accelerate consolidation. Once the pad was secured, work commenced on the foundation, which incorporated hundreds of drilled piers and massive concrete footings to support the superstructure. The building's primary frame featured a combination of steel trusses and precast concrete components. One of the defining features of the stadium, the sweeping roof canopy, was enabled by a network of long-span steel trusses, each weighing several hundred tons. These elements were fabricated off-site and delivered in sequential shipments, where they were assembled using gantry cranes and specialized rigging equipment. The roof itself was a cable-supported ETFE system that demanded meticulous tensioning and anchorage precision to accommodate thermal movement and wind uplift. Inside, the seating bowl was configured with precast raker beams and vomitory walls, each piece carefully aligned to maintain sightlines and support tiered loads. The lower bowl was cast in place, while the upper levels were constructed using a combination of steel risers and precast planks. Mechanical systems were housed in interstitial levels between the concourses and integrated into the structure to reduce noise and vibration transmission. One particularly ambitious component of the project was the operable field tray. Designed to support natural grass for NFL games, the tray rested on a series of rails embedded in the foundation slab. It could be rolled in and out of the stadium using hydraulic motors and steel wheel assemblies, weighing several million pounds in total. This required structural coordination with the surrounding apron and subgrade drainage systems, which had to accommodate both static and dynamic loads without settlement. Facade construction involved a high-performance curtain wall system clad in black fritted glass and metal panels. Behind this outer skin, wind bracing and thermal barriers were integrated to manage the desert climate. Each section of the envelope was panelized off-site and installed via mobile cranes in a rapid sequence, closing in the building in time for interior finishes to commence. Allegiant Stadium represents a convergence of speed, scale, and innovation completed on a fast-track schedule that demanded round-the-clock coordination across hundreds of trade contractors. Rebuilding from near-total devastation, the reconstruction of Tyndall Air Force Base following the impact of Hurricane Michael in 2018 required a complete reimagining of military infrastructure in the face of extreme climate events. The project began with an intensive demolition and debris removal phase, where thousands of tons of structural wreckage, downed trees, and contaminated materials were cleared using heavy equipment including hydraulic excavators, high-reach loaders, and roll-off trucks. Before any vertical construction resumed, environmental remediation teams had to address storm-related hazardous material spills and groundwater contamination risks. Once the site was stabilized, the reconstruction effort shifted toward creating a base of the future, grounded in resilience, energy efficiency, and smart infrastructure. One of the foundational strategies was the implementation of mission-driven zoning, in which facilities were grouped by operational function: flight line, support, administrative, residential, allowing for optimized utility distribution, vehicular movement, and force protection measures. Civil engineers realigned roadways, constructed new perimeter security systems, and raised the elevation of key buildings to avoid future storm surge damage. The new construction used tilt-up concrete panels and hurricane-rated curtain wall systems across most structures. Load-bearing walls were designed to resist sustained winds exceeding 180 miles per hour, and all roofs were anchored with enhanced uplift connectors and continuous load paths to transfer forces to the foundation. Building envelopes included closed-cell spray foam insulation and thermally broken aluminum fenestration systems to improve energy performance while maintaining blast resistance in mission-critical zones. A major focus of the reconstruction was integrating advanced electrical microgrid systems. Redundant power generation sources, including solar PV arrays, diesel generators, and battery storage, were installed to ensure operational continuity during grid outages. Subsurface duct banks were rerouted and reinforced to improve storm resilience, and switchgear facilities were elevated above base flood elevation to avoid future water intrusion. Hangar complexes for F-35 aircraft required particularly high-precision construction tolerances. These steel-framed structures incorporated massive rolling hangar doors, anti-static flooring systems, and integrated fire suppression systems specifically engineered for jet fuel hazards. Mechanical systems included custom air handling units with high filtration capabilities to protect both personnel and aircraft maintenance environments. Drainage was redesigned with sustainability and resiliency in mind. Bioswales, reinforced outfalls, and permeable pavements were incorporated to improve stormwater quality and reduce erosion. Stormwater retention basins were expanded and linked to smart monitoring systems that automatically adjust outflows based on weather forecasts and rainfall events. The reconstruction also deployed extensive building automation systems across administrative and housing facilities. Lighting, HVAC, and security systems are now centrally controlled and monitored, allowing real-time energy optimization and system diagnostics. Residential zones were rebuilt to meet LEED Silver and above standards, using impact-resistant windows, high-efficiency HVAC units, and low-flow plumbing fixtures.
Horizon West Bay in Largo, Florida, is a mid-rise residential development constructed to deliver contemporary living accommodations within a growing suburban city center. Located near municipal and civic facilities, this project is emblematic of the new wave of urban-style residential buildings being introduced to smaller cities throughout the Sun Belt. The development integrates multiple levels of residential units with ground floor amenities and structured parking, requiring the coordinated use of mixed-use construction strategies, efficient structural systems, and infrastructure integration specific to the local climate and regulatory conditions. Construction began with extensive site clearing and grading, followed by geotechnical investigations to determine the bearing capacity of the underlying soils. Given the relatively flat terrain and shallow water table in the Largo area, slab-on-grade construction was ruled out for the upper levels, necessitating a more complex foundation solution. Engineers selected either shallow spread footings or a combination of grade beams and driven piles to support the superstructure, depending on the location within the site and the anticipated load distribution. Subsurface utility relocation was required early in the project, especially where stormwater drainage and sewer infrastructure intersected the future building footprint. Once the foundation was laid, construction transitioned to the vertical structural elements. Horizon West Bay employed concrete masonry unit, CMU walls, for structural partitions and exterior load-bearing components, combined with cast-in-place concrete slabs and precast concrete plank systems. This hybrid construction method balanced strength, cost efficiency, and fire resistance. Interior framing for unit walls and ceilings used metal studs and light-gauge steel tracks, allowing for faster mechanical and electrical installation across units. Mechanical systems were designed to accommodate Florida's humid climate, with each unit receiving a dedicated HVAC system featuring energy-efficient heat pumps, advanced filtration, and humidity control. Plumbing and electrical risers were centralized for ease of maintenance and constructed with noise-dampening measures to minimize acoustic transmission between floors and adjoining units. Fire safety systems included fire-rated walls, smoke alarms, sprinklers, and pressurized stairwells to meet all life safety codes for multifamily buildings. The building envelope was constructed with stucco-finished IFS cladding over a weather-resistive barrier, installed in layers to achieve both aesthetic appeal and energy performance. Window and door systems used insulated, low-emissivity, impact-rated glass to meet hurricane resistance codes while providing thermal efficiency. Roof systems incorporated rigid insulation and a reflective membrane to reduce heat gain and meet Florida's energy standards. Interior work proceeded as each floor was dried in, beginning with MEP rough-ins followed by drywall, flooring, cabinetry, and finish carpentry. Flooring materials included luxury vinyl plank and tile, selected for durability and ease of maintenance. Kitchens and bathrooms were fitted with solid surface countertops, undermount sinks, and energy-efficient fixtures. Common areas such as lounges, fitness rooms, and mail rooms were completed in tandem with residential units to ensure functional amenities at the time of occupancy. Structured parking was integrated into the building footprint, constructed using precast concrete panels and beams with a traffic-bearing waterproofing membrane. Lighting, security systems, and access control were embedded throughout the garage to ensure safety and usability. Site improvements included sidewalks, landscaping, stormwater detention ponds, and lighting fixtures designed for dark sky compliance. Civil engineering played a key role in integrating the development into Largo's municipal stormwater and transportation networks.
The Southeast Connector project in the Dallas-Fort Worth region is a significant transportation infrastructure initiative designed to expand and modernize a key highway corridor to accommodate increasing traffic volumes and improve regional mobility. The construction process begins with detailed geotechnical investigations to assess subsurface conditions across the route. Boreholes and soil sampling guide the design of pavement structures and inform decisions about embankment stabilization, especially in areas with expansive clay or soft subgrades. Initial site work involves extensive utility coordination and relocation, given the presence of underground power lines, fiber optics, gas mains, and municipal water systems. Specialized crews use hydro-excavation and trenchless boring methods to install new utility runs without disrupting surface operations. Simultaneously, the construction zone is cleared of vegetation, existing pavement is milled or demolished, and temporary drainage measures are installed to manage stormwater during earthworks. Mass grading operations utilize GPS-guided bulldozers and scrapers to sculpt new roadway alignments, build embankments, and excavate cut sections through rolling terrain. In low-lying areas, wick drains and surcharge fills are employed to accelerate settlement and enhance long-term subgrade stability. Reinforced concrete box culverts and precast arch structures are installed to span creeks and drainage channels, with erosion control mats and riprap protection placed at inlets and outlets. The highway widening includes adding general-purpose lanes and managed lanes, which requires staged construction to maintain traffic flow. Temporary detours and traffic control devices are deployed in phases, with barrier systems, message boards, and flagging operations ensuring worker safety. Sub-base materials such as lime-treated soil or cement-stabilized base are placed and compacted before successive layers of hot-mix asphalt or continuously reinforced concrete pavement are applied. Bridges along the corridor are demolished and reconstructed with wider spans and higher clearances to meet modern standards. Foundation construction includes driven steel H-piles or drilled shafts depending on soil conditions, followed by the erection of cast-in-place or precast concrete bridge components such as abutments, piers, and girders. Superstructure placement is often conducted during overnight closures to limit traffic disruptions. Sound walls, intelligent transportation systems, lighting, and signage are installed in parallel with the mainline construction. Dynamic message signs, vehicle detection loops, and closed-circuit cameras are connected through fiber optic networks to regional traffic management centers. Upon completion of paving and striping, punch list activities address final grading, landscaping, and system testing before the project is opened fully to public use, significantly enhancing connectivity between southeastern Dallas and central Fort Worth. Where a coal-fired power plant once dominated the landscape in Moapa, Nevada, the construction of the Reed Gardner battery storage system marked a shift toward clean energy storage and grid stabilization. The first phase of the project began with demolition and site remediation. Existing utility corridors, concrete pads, and buried infrastructure from the retired power plant had to be removed or repurposed. Soil testing and grading ensured that the land met the geotechnical requirements for placing a large array of battery enclosures and associated electrical equipment. Once the site was prepared, the foundation work proceeded with a modular strategy. Each battery container, typically the size of a shipping container, rested on reinforced concrete pads designed to bear static loads while allowing thermal expansion. These pads were poured with integrated cable trenches and embedded conduits for power and control wiring. The layout followed a linear alignment to optimize airflow, simplify maintenance access, and facilitate short routing to the power conversion systems. The energy storage units themselves consisted of lithium-ion battery cells housed in steel containers with integrated fire suppression, HVAC, and thermal monitoring systems. These containers arrived pre-assembled and were offloaded using mobile cranes or forklifts, then anchored in place with structural hold-downs. Adjacent to each group of battery containers, power conversion systems were installed, which included bidirectional inverters, transformers, and medium-voltage switchgear. These systems allowed the batteries to interface with the regional grid, converting stored DC energy into AC power during peak demand periods and drawing excess electricity during off-peak times. Cable terminations and system integration require detailed coordination. High-voltage AC and low-voltage control wiring were routed through separate underground duct banks to minimize interference. Grounding grids were installed beneath the entire array, bonded to each enclosure and system cabinet to ensure personnel safety and lightning protection. The site also included perimeter fencing, surveillance, and access control in compliance with NERC reliability and cybersecurity standards. A supervisory control and data acquisition system tied all battery enclosures, inverters, and transformers into a centralized control hub. Fiber optic links and programmable logic controllers enabled real-time monitoring of temperature, voltage, current flow, and system health. In addition to the core storage function, the installation featured black start capabilities and reactive power support to bolster grid stability during contingency events. Beneath the surface of Biscayne Bay, the Port of Miami Tunnel represents one of the most complex underwater infrastructure undertakings in the southeastern United States. Constructed to alleviate downtown Miami's chronic congestion caused by thousands of daily truck trips to and from the port, this project required advanced tunneling methods, massive marine coordination, and exacting safety systems. The overall plan was to connect the MacArthur Causeway directly to Port Miami via twin tunnels, each approximately 3/4 of a mile in length, buried beneath the seabed and designed to handle bidirectional vehicular traffic. Before tunneling could begin, preparatory works focused on dredging and stabilizing the soft bay soils. Extensive geotechnical investigations were conducted using boreholes and cone penetration tests to classify the variable limestone and sand strata that would be encountered. Ground improvement methods such as jet grouting and ground freezing were considered in preliminary phases, but the design ultimately relied on a pressurized face tunnel boring machine capable of navigating both soft ground and denser rock formations. Custom-built in Germany and shipped in segments, the TBM used on this project was over 40 feet in diameter and weighed several hundred tons. Assembly took place in a large launching pit on Watson Island, where reinforced concrete diaphragm walls and a trimmy-placed base slab formed the structural cradle. The boring process progressed incrementally, with the TBM advancing just a few feet per hour while simultaneously installing precast concrete segment rings behind it to form the tunnel lining. These segments, fabricated off-site and transported to the launch area, were equipped with waterproof gaskets and dowel interlocks to ensure tight seals under hydrostatic pressure. The tunnel alignment passed beneath the shipping channel, which introduced unique challenges related to buoyancy, water ingress, and structural reinforcement. At the deepest sections, the tunnel crown lay more than 100 feet below the water surface. To resist both groundwater pressure and seismic loading, the tunnel lining thickness and steel reinforcement were increased, especially at the crown and invert where stress concentrations were highest. Real-time instrumentation inside the TBM provided feedback on ground conditions, face pressure, and segment placement accuracy, helping to mitigate risks of sinkholes or blowouts. Simultaneously, surface-level works included the construction of ventilation buildings at each portal. These reinforced concrete structures house massive axial fans, emergency backup power systems, and life safety controls. Each tunnel is equipped with a full suite of fire suppression systems, including deluge sprinklers and fire-rated wall finishes. A network of electronic signage, CCTV, and incident detection sensors runs the entire tunnel length, all connected to a centralized control room staffed continuously. Upon completion of tunneling, crews moved on to road deck construction, lighting installation, and system commissioning. Pavement was laid using specialized low-sag asphalt mixes designed to withstand constant vehicle loading in a confined environment. Final testing included simulated fire events, emergency evacuation drills, and full-scale load testing to ensure operational readiness.
The Howard Franklin Bridge expansion is a massive transportation infrastructure project aimed at increasing capacity and improving traffic flow across Tampa Bay, connecting Tampa and St. Petersburg via Interstate 275. Originally opened in the mid-20th century, the existing span has faced increasing congestion due to regional population growth, prompting the need for a new parallel structure. The expansion involves constructing a new bridge to the north of the existing southbound span, designed to carry 4 general-purpose lanes and 2 tolled express lanes in each direction, along with accommodations for bicycles and pedestrians. Site preparation began with detailed hydrographic surveys and subsurface geotechnical investigations to evaluate soil conditions and underwater topography. The bridge alignment crosses a broad expanse of open water, requiring hundreds of deep foundation elements such as large diameter-driven piles. These piles were installed using floating cranes and pile-driving barges, often operating in tandem to maintain schedule efficiency. Each pile was driven to a predetermined depth based on load testing and geotechnical analysis, ensuring adequate bearing capacity in the soft marine sediments characteristic of Tampa Bay. With foundations in place, construction moved to erecting the substructure, consisting of reinforced concrete piers supported by pile caps. These piers were cast using custom forms and high-performance concrete mixes designed for marine durability and resistance to chloride intrusion. Superstructure components included precast concrete beams and girders transported by barge from regional fabrication yards. These elements were lifted into place using heavy lift cranes and temporarily braced before the installation of cast-in-place deck slabs. The bridge deck was built in segments to allow for thermal movement, with expansion joints and post-tension tendons providing structural continuity and resistance to longitudinal forces. Given the environmental sensitivity of the bay, strict controls were enforced to prevent turbidity and protect marine habitats. Silt curtains, monitoring buoys, and coordination with environmental agencies ensured compliance throughout the construction process. Traffic staging and coordination with existing bridge operations were critical, as the adjacent spans remained in use during construction. Once the new span is completed, traffic will be rerouted, and the older southbound span is scheduled for demolition. The bridge is designed to current seismic and wind loading standards, with elevated profile grades and robust drainage systems to ensure resilience against storm surge and rising sea levels. Lighting, signage, intelligent transportation systems, and emergency pull-offs are also integrated into the final configuration. The Howard Franklin Bridge expansion exemplifies the challenges and precision required in modern bridge engineering over active waterways in densely populated regions.
The Port Arthur LNG project is a large-scale liquefied natural gas development located along the Gulf Coast of Texas. This mega project, envisioned as a major export facility, encompasses multiple phases of complex engineering and construction efforts aimed at transforming raw natural gas into a liquefied state for overseas shipment. The process begins with site preparation, involving extensive clearing, grading, and compaction of coastal terrain to accommodate heavy infrastructure while ensuring stability against flood and storm surge risks common to the region. Soil stabilization techniques, including deep soil mixing and surcharge preloading, are employed to enhance bearing capacity for future foundation loads. Following site readiness, pile driving operations commence to support the foundations of cryogenic storage tanks, compression stations, and liquefaction units. These piles, typically made of steel or pre-stressed concrete, are driven deep into the subsurface to anchor against settlement and seismic activity. Simultaneously, massive underground utility corridors are excavated to house process piping, electrical conduits, and stormwater management systems. A key engineering challenge lies in the routing of high-pressure pipelines feeding the liquefaction trains, which must be precisely aligned and welded under strict tolerances to prevent leaks and ensure continuous flow. The core of the facility is composed of liquefaction trains, each comprising heat exchangers, compressors, gas turbines, and associated cooling systems. These units transform natural gas into LNG by progressively lowering its temperature to approximately minus 162 degrees Celsius. Modular construction techniques are often employed to fabricate components off-site and ship them to Port Arthur, where they are lifted into place using high-capacity cranes. This approach accelerates assembly and minimizes labor-intensive on-site fabrication. Adjacent to the process area, full containment LNG storage tanks are erected using a combination of pre-stressed concrete outer walls and inner nickel steel liners. These tanks require precise thermal insulation layers and boil-off gas recovery systems to manage pressure buildup. Marine infrastructure, including berths, jetties, and loading arms, is constructed along the shoreline to accommodate LNG carriers. This involves extensive dredging, pile-supported dock structures, and mooring systems designed to handle the thermal contraction of cryogenic loading arms. The project integrates advanced safety systems such as gas detection, emergency shutdown valves, and fire suppression networks. Electrical power distribution is established through substations and redundant backup generators, ensuring operational reliability. Finally, commissioning and startup testing involves systematic validation of all mechanical, electrical, and control systems before the terminal is certified for commercial export operations. Bridges that span tidal rivers and serve both freight and passenger rail must meet an unusual combination of durability, flexibility, and navigational accommodation. The Livingston Avenue Rail Bridge, a vital crossing over the Hudson River between Albany and Rensselaer, is one such structure, and its planned replacement presents a complex interplay of structural engineering, river hydraulics, and transportation continuity. The existing bridge, over 100 years old, suffers from frequent mechanical failures and speed restrictions, necessitating a full reconstruction while preserving continuous rail service throughout the process. Replacing a movable bridge over an active waterway introduces immediate sequencing challenges. The new bridge will likely be constructed on a parallel alignment to the existing span, minimizing disruption to current operations and allowing much of the work to proceed concurrently. Temporary causeways or trestles may be used for construction access, but these must be carefully engineered to avoid interfering with river navigation and environmental constraints, particularly those related to tidal flows and aquatic habitat preservation. Foundation work begins with driving deep piles into the riverbed to support the new bridge piers. These piles must penetrate through layers of sediment and into competent glacial till or rock, requiring a combination of vibratory and impact driving techniques. In certain areas, drilled shafts or large diameter caissons might be more appropriate due to subsurface conditions or noise constraints. Cofferdams are erected around pier locations to dewater the site and allow for dry concrete placement of footing and pier cap structures. The new superstructure will be designed to accommodate both high-speed passenger and heavy freight trains, likely employing steel through girders or a deck truss configuration to balance strength and span length. Modern design codes require larger live load allowances, greater lateral wind resistance, and robust fatigue life considerations, particularly important given the bridge's expected daily use by Amtrak and other rail operators. The track structure will use continuous welded rail supported on precast concrete ties and ballast, all configured to allow smoother transitions over expansion joints and movable elements. A key feature of the Livingston Avenue Bridge is its movable span, traditionally a swing span. In the replacement design, a modern swing, bascule, or vertical lift span must be selected based on navigational requirements and clearance needs. This movable section will be driven by hydraulic or electromechanical actuators with redundant controls, backed by fail-safe locking systems and real-time monitoring instrumentation. The machinery rooms and operator houses must be integrated into the bridge profile while allowing access for maintenance and inspection. With the latest additions to the landscape of modern entertainment engineering, Universal Orlando's Epic Universe stands as a formidable example of how large-scale theme park development pushes the boundaries of construction logistics and immersive design. Conceived as an expansive new addition to the Universal Orlando Resort, the project required the transformation of over 700 acres of previously underutilized land into a fully integrated theme park environment. The initial phases of the project began with comprehensive site surveying, geotechnical analysis, and land clearing. Crews needed to regrade vast swathes of land to ensure proper drainage and structural stability. Underground utilities, including high-capacity stormwater management systems and electrical conduit networks, were laid out early in the process to avoid costly rework during vertical construction. To accommodate the multi-gate layout, civil engineers mapped out internal roads, pedestrian paths, and backstage support corridors, all designed to handle the anticipated heavy volume of guests and service vehicles. A series of massive retention ponds were excavated not just for water management, but also to act as visual and thematic barriers between different park zones. Construction staging areas were carefully allocated at various nodes around the site, enabling multiple trades to work simultaneously on the various themed lands. Structural frameworks for each land within the park varied significantly depending on the thematic and functional requirements. Steel-framed show buildings featuring complex soundproofing and HVAC systems were erected using tower cranes and prefabricated panel systems. Foundations had to be over-engineered in certain zones to support the enormous static and dynamic loads associated with ride systems, many of which rely on high-speed launches, track-switching mechanisms, or deeply embedded hydraulic lifts. In some attractions, such as those simulating flying or space travel, vibration isolation pads were incorporated beneath the concrete slabs to prevent mechanical resonance and structural fatigue. Mechanical integration posed a particular challenge given the density of infrastructure. Each attraction required its own climate control, power supply, data networking, and life safety systems. Fire suppression, especially in dark ride environments, had to meet stringent code requirements while remaining concealed within themed architecture. Likewise, air handling units were often buried underground or hidden in faux architectural elements to preserve the illusion of immersive storytelling. Exterior theming was a collaborative effort between construction teams, scenic artists, and rockwork specialists. Shotcrete sculpting was extensively used to fabricate mountains, castles, and alien landscapes. Fiber-reinforced polymer cladding was applied to facades for lightweight but durable finishes. Paint crews worked alongside sculptors to apply multi-layered coatings that would resist Florida's intense UV exposure and frequent rainfall. A particularly sophisticated aspect of the project involved park-wide integration of a digital experience layer, necessitating deep trenching for fiber optic cabling and distributed antenna systems. This infrastructure underpins everything from mobile app-based ride reservations to location-aware character interactions.
Located in downtown St. Petersburg, Florida, 400 Central is a significant high-rise residential development that exemplifies modern urban engineering and construction in a coastal city environment. The project is designed as a mixed-use tower rising over 40 stories, integrating high-end residential units with retail and office space on the lower levels. Construction of such a tall structure in a region known for hurricane activity and a high water table requires sophisticated planning, extensive geotechnical assessments, and specialized foundation engineering. Prior to vertical construction, crews excavated and stabilized the site, installing deep foundation systems that likely included drilled shafts or auger cast piles extending dozens of feet below grade to reach competent load-bearing strata. Waterproofing and below-grade drainage systems were critical during the initial stages due to the high groundwater level, necessitating continuous dewatering during foundation installation. Once the foundation was secured, a robust concrete core system was erected using jump form technology, ensuring the rapid and safe advancement of the central structural spine that houses elevator shafts and stairwells. Floor plates were constructed using post-tension concrete slabs to provide both structural efficiency and open interior layouts, with each floor carefully poured and cured in sequence, supported by a carefully orchestrated system of formwork and scaffolding. Given the height of the tower, wind loading and lateral forces presented significant design challenges. Structural engineers incorporated a combination of shear walls, outriggers, and a tuned mass damping system, if required, to manage building sway and ensure occupant comfort during high wind events. Cladding the exterior involved the use of high-performance glazing systems and curtain wall assemblies engineered to resist impact and water intrusion under extreme weather conditions. Mechanical, electrical, and plumbing systems were integrated vertically through centralized risers, while HVAC systems were selected to maximize energy efficiency and humidity control critical for the Florida climate. Interior fit-outs followed once the building was topped out, involving high-end finishes, smart home integration, and amenities such as fitness centers and rooftop lounges. Elevators, fire suppression systems, and life safety features were thoroughly tested and certified. Throughout the build, logistics were managed within a dense urban setting, requiring just-in-time delivery of materials and strict adherence to noise and traffic mitigation protocols. 400 Central stands as a prime example of modern high-rise construction adapted for the coastal southeastern United States, blending structural resilience with urban luxury living.